form of the adulteration. So to investigate what are the compounds that makes these hazardous topics in this case, we need to detect in real time and real space, so that it can be utilized in the humanity. So these are anyway the things. So there are various ways of detection. Now, the earlier times with simple observations, they used to detect. At the time, sensitivity was not that great. But now these days we are using the modern day instrument, and we are going for detection and all those things. The requirement of detection is just to calibrate the toxicological impact. And how it is done? Basically, it is done for assessment of concentration threshold, because I always pitch for that nothing in this world is toxic. It's the critical concentration that makes the compound toxic. So we need to monitor all those systems, and basically the detection. So the early form of detection is the color change, basically. So we'll come to that later on. Now there are, as I said, there are various methods are employed for detection purpose. So the basic criteria for effective and ideal detection is it need to be selective. It need to be selective. It need to be sensitive. We need to reproduce the result, and the process can be repeated. It can be of practical utility. So when we use various instrumentation methods at times, am I audible? Yeah.
Yes,
Hello?
Bag, continue.
Okay.
You're audible, continue.
Yeah. So there are various methods which are costly, that require specific protocol to be followed. And alternatively, there is one method called chemosensing, which has now proven to be the powerful tool in analyte detection. And all those things actually we can describe that a molecular system which is having various molecular properties, any molecular properties. It can be structural, optical, magnetic, thermal, mass, electrochemical, anything. It stays in an initial state, but under the influence of external stimuli, light, pH, temperature, or anything, any parameter we can think of, it goes to another state. And the change in the from initial state to final state, if we can measure quantitatively, that serves our purpose of detection. So in this case, I'll be talking about light, I will be talking about chemical substrates, and the molecular properties that varies is the optical one. I mean electronic one, I can say. So describe the whole process when the light falls on a molecular system. So it perturbs some it has some photoinduced function which is getting perturbed by an analyte. The analyte can be another chemical substance which changes the signaling of that property. So that gives the real-time monitoring of analytes, and that can be used in different applications. Anyway, the signaling of that optical property we can have in two ways. One is colorimetric way, other is fluorometric way. Now colorimetric way, we can visually we can perceive it by observing the change in the color. But the fluorometric thing we need to monitor through instrument. And these techniques are to monitor the microscopic changes. Sorry. And they have their own advantage of high sensitivity. They have short response time, very quick. I mean, requires no complicated sampling, and these processes are non-destructive and non-invasive. So a typical design, basically I'm describing the methodology of this topic. So the design of chemosensor is done through multi-dimensional, multi-componential approach, where we have a fluorophore, we have a receptor, and that receptor is responsible for the host-guest interaction, and it has a communication. That communication in the form of photophysical processes, And when there is a host getting interaction at receptor site, so that communication is altered or perturbed or changed accordingly. The functional unit, that the fluorophore, it gives a different signal. And the signal actually we can have in form of appearance of spectrum, emission quantum yield, excited state lifetime, and of course there is a color change, which is easier in any respect. So by seeing that, if a molecular system that exhibits both the color change as well as the change in the emission, then that is definitely advantageous in analyte detection. So when I was talking about fluorescence for the knowledge of the students, I would like to highlight this part, because it has a 450 years, more than 450 years journey. It started with observations of Sagun, who found that in a bowl, wooden bowl of lignum nephriticum, that when water is given poured inside the bowl, the color actually changes into blue. So, and later on, the botanist, the biologist, they actually used that water for treatment of kidney related disease. So that's why initially they called this lignum nephriticum as the kidney wood. The similar observation at the same time was observed by Nicolas Monar, the Spaniard, and then Charles Diaclus or Kircher. Kircher basically documented this part of this lignum nephriticum. And significantly, in 1664, Robert Boyle observed that the blue color is changing again to yellow color when acid was added to it. Anyway, these are the early observations of the color change or the signaling, whatever I'm talking about. But in early 1900s, it was found that there exists no lignum nephriticum wood, basically. And what Sagun experimented with Pterocarpus indicus, what we called the snake tree in Indian subcontinent, and the other one is Mexico one, which was observed by Monardes. Anyway, those are these things. Then there was various observation of emissions. The significant one was by Galileo, who observed that the emission is coming out of the Bolognian stone. I mean, it was Vincenzo Casariello actually observed that phenomena, the shoemaker Vincenzo Casariello. Anyway, I mean, it has a separate history of that one. That fluoride emissions from fluoride, emissions from chlorophyll, all those things were observed. Then John Herschel actually he found the emission from quinine sulfate. Then Stokes basically he termed this at the time he termed it dispersive reflection, this phenomena, and later on he himself said that he didn't like this term dispersive reflection, so he changed the term to fluorescence. So these are the history of fluorescence. Then there are various significant contributions to the field. If you can see that Perkin has the first synthetic dye, then Gopal Stoddard was the first to use fluorescence in detection technology. I mean, detection of aluminum in a solution. Then first dye spectrum was recorded by Nicola Merritt. Sternberger has contributed in fluorescence quenching. Jais Richard, they have developed the fluorescence microscopy. Then Vavilov Levson, Vavilov particularly is credited for the fluorescence quantum yield. Perrin, he gave the theory of fluorescence polarization, was what Vavilov and Levsin has observed through experimentally observed. Then all those things, and famous was the Jablonski diagram, who gave the molecular basis to this process. and Foster, of course, given the dipole-dipole interaction, and many more. So the fluorescence is basically with a 450 years what to say research on this particular field is used as a detection what to say output in chemosensing technology. So coming to our kind of work, we are using the rhodamine-based fluorophores. Of course, this is also nothing new. I mean, it was first synthesized by Ceresol in 1887. Then the equilibria was established at 1956. Solvent effect by Levsin, toxicology Webb, and significantly the metal ion detection in by Jarnik in 1997. So what is so significant about this particular molecule? Because this any xanthine dye system, because of this spiroring, uh, this compound is colorless and non-fluorescent. But when it structurally equilibrates under any external stimuli, the spiroring gets opened up, and in this form, it is giving a color and it is highly fluorescent. This compound is mostly preferred now these days for at least for past 20 years, after the 25 years after the Anthony Janik's observation of in molecular and metal ion detection. I mean to say, it has several advantages of absorption, emission at longer wavelength, high quantum yield, and all those things. It has a structure function correlation. It has a capability of having this dual mode signaling in operating in aqueous media, and it is synthetically very easy, and it is stable, and it has low photo bleach and all those things. And because of this, actually, we have preferred this molecule because it is low, I mean, economically very viable. The first use of xanthine-based system in the detection methodology was done in 1877, basically, because those who have went to Europe and went to Black Forest, you can find a place where there is a confluence of two rivers, Danube and Rhine. So the geologists of those times, they wanted to know whether there is any undercurrent between these two rivers, because one is at a higher altitude, one is a little lower altitude, but they start from the same point. So if there is any undercurrent, so for that purpose, they used 10 kg of, they used at the time they used fluorescein. Actually, fluorescein was synthesized by Bayer, and so they used that fluorescein, 10 kg of fluorescein, put it in one river, water of one river, and they found that the traces of the fluorescein in the other river. So they proved that there is an undercurrent channel between these two rivers. And with this experiment, those fellows, the Ceresol and where they became millionaire and all those things. Anyway, those are the topic of a separate talk. So coming to this, then we experimented with various photophysical signaling of these kind of molecules for and first we used for metal ion detection, basically. So we found that metal ion under certain condition, actually they open the spiral ring and gives the signaling. It can be of the chromogenic, where the absorption is getting high, or it is fluorogenic, where the fluorescence is very high, and it gives different color. So it behaves, it gives signal, I mean the extent of enhancement of those signals is different with a different metal ion. But to be a ideal detection probe, this has to be selective. So for that, we experimented with many different conditions, different metal ions and all those things. So this is a design of a typical experiment. I'm not going to explain each of them. So in this case, we can see that there is absorption enhancement, there is fluorescence enhancement, there is a change in the excited state lifetime, the Gauss plot which shows the how much what is the stoichiometry of complexation, and there is selectivity experiment, kinetic experiment, the reversibility experiment, because until and unless a molecular probe comes back to its original state, it cannot be called as a sensor because we cannot use them. And all these things are supported with the theoretical investigation. So what I am discussing here is the methodology, how we need to tune them to get the desired whatever we want to have. So with various metal ions, we went on doing these experiments and the observations. We found that when this kind of molecule is substituted with electron donating character, basically they give selectivity towards mercury. Of course, there are a few deviations, but anyway, that depends on the electronic environment, the stereoelectronic condition of that molecule in that particular solvent. So when an electron withdrawing group is attached here, in that case, it is primarily giving the selectivity towards iron. So this gives that what makes this kind of molecule selective towards mercury or iron. One is D10 system, one is D5 system. So for that, actually we carried out all these experiments to understand what makes this kind of molecule exclusive for mercury ion. So these are anyway typical this thing. So we found that there are various factors actually involved in that. First thing is the size effect, because if we go through the Martel-Hancock theory, if the bite angle is more, then it binds to a smaller binds to a metal ion which is having a smaller radius. If the bite angle is less, it kills to a metal ion having a higher radius, I mean higher in size. So there are core electron involvement and the redox potential, everything actually favorably uh, suits the chelation of mercury towards this kind of molecule having the amino 2 amino group, and basically it's a host guest chemistry problem. So we have shown that these factors actually favors the mercury binding to this kind of molecule. So this we term as a stereoelectronic configuration. Then the solvent plays a greater role in mercury selectivity for this kind of molecule, because we found that aqueous component in the medium, it introduces the selectivity. From this spectra, we can see that okay, it is responsive to various metal ions, but in this spectra where the solvent is aqueous acetonitride, in that case you can see that it is selective towards only mercury ion. So that anyway we determined that it all depends on the dynamic equation between the hydration of metal ion, hydration of the probe molecule, then the metal probe ligation, then the solvation of metal ion, solvation of probe. And for mercury case, the enthalpy change of mercury probe interaction has to be more than the hydration enthalpy, solvation enthalpy of the metal ion, and hydration enthalpy, solvation enthalpy of the probe. And it has to be the enthalpy of this probe metal interaction has to be greater than combined of all these things. But in other cases, for other metal ions, the enthalpy of metal ligand interaction is less than the other enthalpies. So this was our observation. So this functionally contributes towards the selectivity of these kind of systems. Now there is one more observation where we found that initially a metal ion binds because of its affinity towards that particular probe, depending upon the stereoelectronic environment of metal for coordination. Then later on it get detached, and the other metal ion, it really binds to it. So that's how the kinetic experiment shows that it has the contribution from the kinetic part also. So with all those experiments, so we can say that if we wish, we can tune a particular molecular system towards detection of a particular metal ion by varying the stereoelectronic environment, the electronic interactions between metal and the probe, and all those parameters. And those parameters are driven by the structural, functional, and kinetic contributions. Here is one example where we found that okay, once one metal ion binds to a particular probe, it helps the other metal ion, I mean other atom, the other ion of the same metal ion to bind faster, and that is how we define it, the cooperativity. Now for mercury, we know that the mercury has a affinity towards sulfur. So because of the soft interaction, we all have studied in HS basic principle that mercury prefers thiol kind of molecule, and because of that there is a cooperativity in this kind of system. Anyway, let us not discuss more about this, but yes, for improving the sensitivity, we need to go for racemeric signaling, because at many times the single molecular output unit is influenced by various environmental parameters. So in that case, racemeric signaling actually helps in. So for that also we have used the freight mediated processes. We developed the molecules which is having two fluorophores, and the ratio of their intensity actually gives a stable signal towards the sensitivity of the system. These are the few examples, I mean, of this thing, towards contributing towards sensitivity. Now one more interesting observation for us, that no matter whatever the number of publications have appeared in literature, all were working for 5-member spiral ring. So we thought let's go for a 6-member one, why not? But our observation was like 6-membered spiral ring, they are selective, but they are not that sensitive as it used to be in the 5-member spiral ring systems. So again, I was talking about to be talking about the reversibility, because to be called it as a good sensor, it must have the reversible property. The spectral or the output signal comes reset to its original state. So we found that by addition of counter anion actually helps the ring opened spiral, that rhodamine based probes goes back to the spiral ring system, and the initial output parameters, those are reset in that case. So here is the detection of amino acids through metal ion displacement approach, and it all depends upon the affinity of that probe with the incoming guest. Then nitroaromatic detection, because there are various methodologies actually, like for detection of aromatic phenols basically. So Some says because of this proton, some says because of this pi interaction between the probe and the guest, this nitroaromatic. But in this case, we have found that it's a the if the pK of the acid or the base, they matches. So in that case, it helps in opening up the spiroring, and we get the fluorescent signal. So those are the various cases that how to tune the selectivity in this kind of system with the help of different different heteroatomic systems. So basically, all these I'm trying to explain that as per our own requirement, we can tune a molecule to detect a particular metal ion through a specified host guest based chemistry, and we can vary the signaling amount also through the sensitivity of that detection. Now these are the various questions actually we have to ourselves. If the long chain alkyl which has having the electron donating tendency to a amino system, whether it has any effect on the opening of this spiroring of this kind of system. Basically, we found that no, it doesn't have such kind of hypothesis, or it actually fails in that to prove that whether that electron drifting of electron density from a alkyl chain to the nitroatom really helps in the signaling of this kind of molecule. So this is one more example I would like to give, that detection of organophosphates, because I was talking about the Novichok agents and all those things. So we found that in many cases, in general tendency, if we'll go by this schematic diagram, in general tendency, where the receptor at which the analyte binds and the photophysical perturbation occurs in those places, those are the indirect way. In this case, we have shown that the analyte, this organophosphate, binds directly to this this carbonyl of this spiroring of this rhodamine based system. This actually is important because if we'll discuss a bit of chemistry, that it gives a Abramov product through an intermediate, I can say, because Abramov product, where the phosphorus center is very electron rich, like oxysiloxy phosphorus compounds. The P and this carbonyl C bond occurs fast, then it translates with this equilibrates with this oxygen, but in this case it directly binds to the phosphorus of this organophosphate. Anyway, we can discuss that chemistry later on. So this is our latest effort on this hypochlorous acid detection and all those things. The principle is same, the methodology is same, just the variation of electronic environment of that probes. So these are in solution, but we didn't restrict ourselves to solution also. Then we went for solid state detection. In that also we have seen that in solid state also, these kind of probes, they are capable of interacting or giving this kind of signaling. And when it is used in the removal process, removal of that particular metal, depends on the size of the substrate on which the organic part is functionalized. Anyway, we can discuss all these later on. And these kind of molecules can be used in various ways. One is localization of bioaccumulated metal ions. We have experimented with various roots and shoots of various medicinal plants, Arabalanata and all those things. Everywhere we can find that the uptaken metal ion by that particular plant can be detected with this kind of molecular probes through similar the structure function correlation mechanism, the opening of spiroring and all those things. So these are the few more examples on this. Now, with all these experimentation and all those things, whether this kind of system can be translated into a device making. So with the help of our colleague who works on electronics, we found that, or I mean, the photophysical signal, the signaling, I mean, switching off to on, or the enhancement of photophysical signal indeed can be translated into the electronic signal, and we can have the electronic output of this particular photophysical perturbation. Anyway, this work is unpublished, and we are working on it for better sensitivity. So basically, in all these experiments and all these data I have shown, basically I wanted to show a methodology that these kind of molecules are the potential chemosensors for various analytes, where the molecular design is based on the targeted analyte, and in other way also we have a probe, and we have to investigate what kind of analyte it can bind, so that it can change its absorption, fluorescence, or color on host guest interaction. So the structural and functional entity contributes significantly for induction of selectivity. That's what I was talking about. That in principle and on a methodological paradigm, various ensemble can be tuned for selective detection of various metal ions, various analytes, particularly the organophosphates, which we are still continuing. And this kind of work, of course, we are going to continue. So I would like to acknowledge our institute, then the actually the workforce who has proven this kind of systems, for whom actually I'm just explaining all those things. My students actually, uh, I'm able to explain all these processes and all those things. And few of my teachers actually who helped me during the initial days of this kind of research, and the funding agencies. So basically, I can say that color are interesting, but more interesting are the philosophies on the chemical processes of color, and we can have a discussion on this. But thank you for kind attention.
Thank you, Dr. Bag. Now the topic is open for discussions. Any queries? Any questions?
Ma'am, we can discuss all these if anybody can interested. I mean, through email. My email is bpbag@immt.res.in.
Yeah, that can be done. But now if anybody has any questions, then they can ask. We can allow 1 to 3 questions, because 2-3 minutes we can take.
Hello.
Yeah.
May I put a question?
Sure, sir.
Yeah.
Always when we talk of detection of mercury or lead, we would like to always ensure that there is no interference
Yes.
of any other competitive ions.
Yes.
So in this case, I find that iron is very closely competing with, not very closely, but it is really coming into picture. Iron. So
Yes.
iron is present, its concentration in normal water is very high, compared
Yes.
to mercury. So in that case, when the sample contains large quantities of iron and a very small quantity of mercury, does it work?
Yes, first is like it all depends on the probe design. Oh, we have shown that when I mean in this kind of rhodamine based system, when an electron withdrawing group is attached as the distal amino group, that is selective towards iron. But when an electron donating group is attached, and based on various parameters, those kind of molecules are selective towards mercury. So in that case, no matter what is the amount of iron is present in the system, it will selectively bind to mercury. Of course there will be the interaction, but that again we can remove through these solvent parameters, because if we'll do in the aqueous system, and if there is a iron and there is a mercury and this kind of system, so as I have shown the enthalpy chart for mercury, we can tune that so that the enthalpy of mercury is higher in this case than the rest of it. But in case of iron, actually the salvation energy of iron plays a greater role, or the hydration energy of iron plays the greater role. So for this kind of system, yes, we can tune, and it can selectively detect mercury.
Okay. Have you made any patents on this?
No, no, not yet. Actually, we are working for that electronic device, and after that, actually, we'll apply for patent. Maybe in this year. So,
Right. You should do it. Yes. It seems good.
thank you, sir.
Yeah, I have a point to mention here.
Sure, sir.
Uh, let's say mercury and iron. Now, out of these two modes of detection,
Yes,
a fluorescence and absorbance measurement or observability measurement, between these two, for mercury, probably fluorescence technique will be better suited because generally mercury doesn't absorb in the visible region,
yes,
but the fluorescence of the complex or
yes,
the fluorescence of the ligand bound to mercury will have a uh, choice for its estimation or for detection as compared to the iron system. Iron system can be useful for both the things as fluorescence as well as absorption technique. A
yes,
suitable ligand
yes,
when we are using a we want a choice for a particular ligand, the fluorescence technique will probably act better for
yes,
mercury than
yes.
for iron.
Yes, sir, that is true. Absolutely true, sir. Absolutely true, sir. And with fluorescence, actually, we are getting the higher sensitivity for mercury, and we can detect up to, I mean, less than 2 ppb. It's 1.6
Yeah,
ppb
yeah,
mercury we can detect with fluorescence.
yeah.
But iron, we are unable to get that much
That's right. That's
sensitivity. That is true. You are true, sir.
And lead does not interfere. Sorry, sir. You are still going on with the question, sir.
lead can interfere because lead is practically colorless in the, I mean, if it is colorless, it can interfere. But between mercury and lead, one has to see which forms a stabler complex.
Yes.
That's
Yes.
very important also.
Yes, yes, yes. So again, that depends on the ligand
Yeah,
design.
environment.
Yes,
Yeah.
yes, sir. That is true, sir. Thank you for the suggestions.
So if there is no more question, let us thank Dr. Bag for a very interesting topic and welcome Dr. Prasanna Kumar Sahu
Thank
for
you.
the
Thank you.
second invited talk. So our second invited talk will be delivered by Dr. Prasanna Kumar Sahu. Material Science Center, IIT Kharagpur, and the topic is low dimensional semiconductors for optoelectronic and sensor applications. So here is the brief biodata of Dr. P.K. Sahu. P.K. Sahu is an experimental condensed matter physicist with a broad experience in the study of different low-dimensional materials. He obtained his PhD degree from Homi Bhabha National Institute, and he spent several years at the State University of Campinas, Brazil, University of South Florida, USA, and University of Cambridge, UK. Then he joined as assistant professor at the Material Science Center, IIT Kharagpur. Dr. Sahu's work covered various areas of nanomaterials that include 2D materials and heterostructures, Group 3 and Group 5 based semiconductors, nanowires, and sensors. His current research focuses on the exploration and understanding of exotic 2D materials and their heterostructures, which have fundamental and wide range of technological implications, heterostructuring, spectroscopic, characterization, and device fabrication for physicochemical properties assessment. Welcome, Dr. Sahu.
Okay, thank you very much for the invitation. Okay, so, and also for the organization and inviting for this talk, although I am a bit from a different background. So I'll try to make my talk in such a way that most of the students can get a flavor of what kind of work we are doing here. Okay.
So this talk will be for 45 minutes.
Okay, perfect.
Okay, you try to finish within 45 minutes.
Yes, fine. I will try to finish before that.
Okay.
So I don't know, a lot of things are popping up in between. Do you have any control to stop that?
No, I think not possible. Please go ahead with whatever.
Okay, it's fine. So my talk will based on the low dimensional semiconductors, like nanowires and two-dimensional material like graphene-like materials for optoelectronics and sensor applications. So why we need, although we have a lot of bulk materials and if you go to market, you can readily buy many things. It's a low cost LED, all things. So why we need a new generation of materials? Because now everybody are more passionate for electronics, which need to be flexible, transparent, and high performance. At the same time, it should have ultra thin body and devices so that we can wear it. We can make smart watches, we can make smart glasses, smart tablet, and smart mobile like things. And also we can make some kind of flexible biosensor that can communicate in live in situ our health condition to the nearby doctor of our interest. So, and another aspect, and apart from other application, one can think about now today the world is full of Wi-Fi signals. Can it possible to harvest this Wi-Fi signal into energy so that we can power our small scale devices, electronic devices? That's the target. In that context, these low dimensional materials and two dimensional material will be very useful. So another big exploration is the solar cells materials. So one can see here the time currently from the Swiss company, they're trying to make a low cost solar cell materials so that they can use in a solar aircrafts. So they already made a demo so that in that kind of, if you compare this kind of a small scale airplanes with that of Boeing system, which can carry nearly 700 people, but here it is a proof of principle based demonstration where we can use solar cells to harvest energy, and the same energy can be utilized to run the system. But major drawback, the present solar cell based systems have some masses, and the overall weight reduce the performance of this kind of system. So that in that context, what we also need a new generation of solar cell materials that can be lightweight, at the same time it should have high efficiency. so that we can achieve the above said objectives. So this guy is asking how we can develop then that. So how we can develop a smart and efficient future technology. So he's saying, oh, I will use 2D materials and their heterostructures like graphene and beyond. So in another couple of slides, I will give a brief introduction about what is 2D materials. So in terms of understanding the physics of each of materials, how we classify certain materials in a particular, like one is 0-dimensional, 1-dimensional or 2-dimensional materials. So it is effectively the density of states. That density of states talks about how electronic orbitals in terms of a chemistry picture, how they in the momentum space they occupy inside the materials. In bulk materials, like 3-dimensional materials, like you observe in common like gold or something we're wearing here. So these are commonly classified as 3-dimensional materials where there is a continuous change in the electronic density of states. And in a 2-dimensional material, what happens, imagine, as if you have a restriction in one direction. The carrier can only move in X and Y plane, and there is a restriction to move in the vertical axis or in one plane. That time we say that it's a 1-dimensional confinement, but it is called a 2-dimensional materials. But similarly, and here the energy states are like step-like function. That means up to a certain energy level, only there a particular energy state will present. That's the reason. And in 1-dimensional nanostructure, that means you are restricting the material motion or the carrier motion in X, Y or some 2 direction, and the carrier can move only in one direction. That is like a one-way traffic. So you just move in one direction. So that is called our nanowires. So in nanowires, we have like this kind of density of states, electronic states. And 0-dimensional material means you confine the carrier in all 3 possible directions. So that carrier is literally confined to a particular space and its electronic density of state. So this is how we can classify different materials. So in today's talk, I will mostly focus on this kind of 2-dimensional and low-dimensional materials. There's some noise from background. Could you please mute yourself? Okay. So the basic difference in bulk material, to give a layman idea about what 2D material is, you can think about a potato types. In potato, if you want to slice it and to make a thin layer of materials, what you have to do, you have to literally chop it from layer by piece to piece. But because, so you can see atoms are a 3-dimensional arrangement in space. So there is a covalent bonding between different layers. So you have to break these bonds, you have to literally, you have to put a lot of force, or you have to dump a lot of energy, to break such kind of a covalent bonding system. But there is another kind of materials, you can think about onion type. So there you can peel out one layer by layer. So this is exactly the idea used by the Nobel laureate Andrew Jim and Novoselav. So they can initially from graphite, they peel a single layer of materials. And that's all about the story of a 2D material that gives rise to a tremendous opportunity to explore the physics and the chemistry and engineering aspect at that low dimension. And the field is evolving at faster rate than ever thought of. Okay, so what is the basic difference between this bulk 3D and this bulk 2D material? So there is a covalent bond, and here in the bulk 2D, so there is a van der Waals bond between different layers. And since van der Waals bond is energy involved in this process is very low, that's why you can easily pull it out. Okay, so in bulk, and another aspect, you can see the surface is terminated with a lot of dangling bonds, but in 2D it is atomically flat surface. So there are some positive and negative aspect of it. Suppose one is looking for developing a sensor like gas sensor or some aspects. So this material can be good because it can provide ample side for the atom to sheet on that or fidget over the surface so that it can contribute to the change in the electrical or optical or this kind of magnetic so far. So many depend upon the type of application or sensor one is looking for, so the properties can vary. But 2D material, it can provide a perfect opportunity to make a flat surface and smooth surface. And there are not only, and this family is really broad. We can find insulator, graphene like semi-metals. You can have semiconductor, so that we can complete a story. And if you want to make a device out of it, so what we need is all kind of different material, dielectric. We want insulating materials, semi-metals, and semiconductors. And semiconductors are so widely useful for a varieties of applications, including optoelectronics, is part of it. So in this talk, I will discuss about we move one step further and to make it this kind of lateral heterostructures of is like we can able to control atoms in few layer. So we can make 3 atom thick, and at the same time we can make heterostructure. So we may grow one material, and the edges of the first material we can make another layer, and we can sequentially control the growth in lateral direction. That's why we call lateral epitaxy or lateral heterostructure. And what I will, in through this talk, I will show you how it is beautiful to change the phase, to change their charge, to control their spin and all sorts of physical properties at this low dimension in order to observe some exotic properties, such as some optical behavior and some unique excitonic effects, and solar room temperature and room temperature light emitting diode we can realize using this atomical thin surface. This is all about my work in this here. And our greatest contribution in this field is, you can see here, we publish a nature paper on this, where we can use different kind of heterogeneous materials, bulk powder, and we can simply use some carrier gas, we can switch so that we can grow one material at a time in order to realize direct synthesis of 2D lateral heterostructure. Okay, so there are some physics, more on physics term. I'm not going to more details about it. So what I'm in summarizing is that this field is really very emerging, and there are many new discoveries are still awaiting in this field. So to give an idea about the structure, that which is very important before going to talk more about the heterostructures. So these layered materials, these are transition metal dichalcogenides. These are basically in the form of MX2. M is your metal, molybdenum or tungsten. X is your selenium, sulfur or telluride. So the unit cell is looks like that. So, but when I say monolayer, so this monolayer is a 3 atom thick, and the middle atomic layer is mostly made of a transition metal, and the top layer and or bottom layer, it is like a sandwich, like a burger, and you have a meat in between. Your meat is your transition metal, and your bread is your chalcogenides. So that sandwich effectively the thickness is of only 3.3 angstrom. Okay, and the beauty of this material is even though the total thickness is 0.6 nanometer, but the absorption per monolayer is almost 10 to 20%. Well, that's why it creates a whole lot of new application, because for 3D material, if you thin down to a few atomic thick, it will almost absorb nothing, because absorption is also dependent upon the amount of material present. But this metal have some peculiar effect. Why it is so in terms of physics, and in in the chemistry they will talk about more on orbital how they interact, but in terms of physics, how will explain that? For mostly for semiconductor, we have a conduction band and we have a valence band. Like, so if both conduction band minimum and valence band maximum, if they stay at a single k point in the momentum space, so momentum space indirectly talk about how directly one electron can jump into another place, means conduction band to valence band. If they both are in the same momentum, like jumping within the floor and out between building to out of another building. So it is easy to jump within the building than to jump from two buildings. Those are specially apart. Okay, that's how the direct band gap semiconductors matters. Okay, in this bulk semiconductor of TMDs or 2D materials, they are mostly indirect band gap semiconductor. That means these are not energetical favorable for the transition process to occur. But the moment you thin down to a single layer, so what you can see, the conduction band minimum and the valency band maximum, they lie now at a single momentum space or in the single direct transition is there. That's why that means is optically more active. And the electron or the photon can interact directly, and the overall quantum yield will be better as compared to compared to bulk. That means your bulk is not very effective for optoelectronics like laser, LED, or solar cell. But if the moment you thin down to single layer, this will be more effective as compared to bulk. So I'm not going to talk more on the graphene. Graphene, just to give an idea, in graphene, the valency band and conduction band are just touched at like direct points. Okay, so that means they can carrier can diffuse ballistically. In boron nitride, there is a wide band opening, that's an insulator. On this TMD, there have you can see the valency band is degenerated. That give rise to another moment, degrees of freedom, and the field of electronics, all things came into picture. Okay, so another important aspect, this is a more physics term. I am not going deeper on that. Exciton. Excitons are like electron and hole, positive and negative charge, and they, when you are exciting, they form a bound particles. And once they form a bound particle, they can now freely move along the surfaces. Like when you are shining light in a semiconductor, what happens? That light will trigger the emission or trigger the movement of a or generation of a carrier. It can be electron or a hole together. That electron now can combine with a hole, and that can form a exciton. And what is interesting is that in this 2D material, in the TMD, the binding energy of this exciton is really large. You can see about 450 megaton-volt. That means they itself stable at even at a room temperature. That means we can make in future exciton based this kind of things. And very recently, so okay, so let me discuss about little bit under this exciton. It can also combine with another carrier like electron or hole that can make trion, bi-exciton like that. Very recently, we also discovered about the polaritonic trions. And okay, so this is a different context. So is another field is emerging is that suppose you have a single layer of this 2D material and you stack another layer. What you see here is a creation of artificial lattice, like it's not existing their counterpart, but only when they align in certain way they can form this kind of periodic pattern. And this is why they sometimes harvest or they can interact with their surrounding in a different way. They can trap electron holes, exciton at a particular site. They can emit, like they can use as a quantum emitter at particular locations. Okay, we can whole lot of, we can control their directional things so that we can manipulate their phase in more effective or a wider range. So how can hide this part? It's always hiding my top sections. I don't know.
Really?
Okay. Fine. So this is all about in the periodic table. You can see the how many number of transition metals, and these are diodes and chalcogenides, selenium, sulfur, telluride. So we have a wide range of combination. In this 2D family of materials, we can have graphene-like family where we have semi-metals, insulator, all these, and we have semiconductor types or metallic types. So where we have semiconductors, and we have these also different kind of semiconductor. Metallic will be good for catalysis or those kind of application, battery, all those applications of this 2D material. Okay, mostly today I will focus on the semiconductor-based 2D materials. So before going to talk about heterostructure, what is a heterostructure? Heterostructure is a combination of different heterogeneous materials. So one material and you combine another materials, so they have distinctly different properties. So that, and you combine another A, suppose your A material, a band gap is like that, and you could attach another material with the band gap less, so that you can trap carrier in a different way. This is the basic principle of many laser or LED. And for solar cell, your band alignment should be like that. If some of you have a chemistry related topic, you know how the overall in respect to in more in chemistry term, it is they always correlate with the normal hydrogen potential. It's similar way. How the potential positions or the band position are aligned, that will determine how the carrier will transfer from one material to the other side, or how effectively that will occur. Okay, so there are different way we can arrange materials. So we can see why this low dimensional material is important is in a bulk material. For example, if you want to look for solar cell, if you want to make a device, your carrier have to diffuse. Like you can see the depletion region when you attach a N-type semiconductor or a P-type materials. What will happen as if there is a crowded region in between? So that means if the carrier want to go to this side, they have to literally go into a crowded place and cross this region to other region. That is called depletion zone. What if you make 2D materials? Because there now it is ultimate thickness limits, so there is no this kind of diffusion process. Diffusion process involve more energy, because imagine if you are in a shopping mall and there are a lot of crowded people, and one of your friend is standing in the other side, you want to go there, so you have to literally break the bond between many people and go there, right? Same way it happens to the real life in the 3D materials. But in 2D, the carrier can tunnel. No, there is a just you can just jump to the other place, so that it is a very with less power you can make your devices. Your connection like neuromorphic or neurosensor, all these kind of things you can do effectively with low power. So how can make this kind of structure? Please remind me before 15 minutes before finishing, so that I can speed up accordingly. So how can you make same thing like toys? You can combine different kind of material to make heterostructure. So imagine the first materials like for heterostructure, it is now it is allowed mechanically. You can exfoliate single atomic layer. We can stack them into this kind of many configuration. Sometime now our technology is capable to peel off a single layer and stamp it in the vertical direction. But imagine if you would like to make this kind of heterostructure in the lateral direction, like in plane, that means it is not possible to go and stitch atom by atom. By our technology will not allow. That means we need a synthesis technique where we can create this kind of lateral heterostructure directly. This is where our expertise lies on that. On this field was recently progressed in 2014-15 onwards. You can see is a very new field. In this field, there are several drawbacks to make, like how you can control grow in a lateral direction. This is where my greatest contribution in this field, where we can find a simple method like a water and hydrogen. Water is behaving like a oxidizing agent, and hydrogen behave like a reducing agent. Simply by changing the carrier gas from water rich environment to hydrogen, I can able to switch the growth of material from one side to other side. So here you can see we can make all are laterally connected like this one. You grow one material, then you stop the growth of one material and you grow other material. Then you can continue like that. You can indefinite number of domain you can control. Their thickness is, remember this thickness is one layer, means thickness is just a half a nanometer, like 0.6 nanometer thick. But we can see the contrast because the absorption is almost 10 to 20% is a monolayer. So we can easily see that in optical microscope. You don't need high-end techniques to see that. Okay, so this is where this technique we call chemical vapor diffusion, where in chemistry Chemical means a chemical reaction occurs. In the standard concept apply like thermodynamics, kinetics, all these concept apply. And V is referred to precursor. Vapor is a precursor. When you put some solid precursor here and you heat it up to more than 1000 degrees Celsius, what happens? The material can evaporate. Literally everything can evaporate. And depend upon you to find its evaporation temperature. And once it is evaporated and at a lower temperature side around 800 degree, this vapor again can condense and form the crystals. So okay, that's how the concept of deposition rate, substrate effect, catalysis, and roughness all they come into picture. So we can see here in the literal initially whatever the vapor it will evaporate, so it will form first a catalytic or nucleation site. That nucleation site can further the atom can come and merge on the substrate that can grow on the bigger substrate, bigger crystal. Typical in our method like CVD techniques, you have a carrier gas like argon and hydrogen and nitrogen, and some percentage of nitrogen you bubble through the water vapor so that it can carry some water moisture in it. And here you put a bulk powder like MOS2 and WS2, and when it at high temperature, when water vapor interact with the this kind of 2D material, that because the molybdenum and tungsten they behave differently because of the distinct behavior of this transition metal with that to water and hydrogen. These we can uniquely control their amount of vapor precursor. Okay, so that I can show you sequentially. But you can see before going to the mechanism or the bulk powder like MOSE2, if you interact with the water and the hydrogen, what you can see that these are called Raman spectroscopy. Raman spectroscopy, you give a Raman like IR, but in Raman we can give information about the fingerprints of a particular material, what the type of material is there. When you interact with the water vapor, what happened interact with the MOS2 surface, and it gave a lot of chemical reaction happens, and later on it can generate some MO2, molybdenum dioxide, that you can identify from the Raman spectroscopy. Same thing, either you take MOS2 or MOSE2, but at the end selenium evaporate and it from MOO2. But we can see somebody from tungsten, it is a pure metal, when it's interact with the water, they don't change too much color. But if you interact with the water for prolonged time, we can see this kind of secondary phases evolve. So what you can see, bulk WSE2, you have a single Raman peak, but eventually when you interact with the water more and more, this form a lot of different level of sub-oxides, and that give a dynamic role towards the growth. You can see W20 to 058, that means more different kind of sub-oxide forms, and if it what it tries to go to achieve its most stable condition like WO3, like tungsten trioxide, which is the most stable phase of the tungsten oxides. And Raman is also give a very idea, suppose to validate what is the role of the water and hydrogen, what I choose the molybdenum or this kind of molybdenum oxide, molybdenum selenide, tungsten selenide, and WO3, and interact the water. What drastically you can see here in case of MO2, this is this is effectively reduced drastically. 99% of material they just interact with the water and evaporate immediately. But tungsten is stable. It is tungsten oxide that don't evaporate at all. That means even at 1060 degrees Celsius, so if you interact with the water with the molybdenum or tungsten, they behave different. So molybdenum evaporate immediately, but tungsten don't evaporate at all. Same time when you interact with the hydrogen, so molybdenum deplete rapidly, but tungsten deplete slowly. And because of this peculiar behavior, so they contribute to the growth in a unique manner. So you can see very nice image how the phase change occurs. Suppose you have a MO3, You interact with the water, you can in 1 minute, it can form different kind of suboxide. You have suboxide, you have a different kind of color. So slowly, slowly it can deplete and form metal color, completely deplete to metal. But tungsten, you can see in 10 minutes from tungsten dioxide, it will go to up to maximum tungsten dioxide. But in it, within 10 minutes, total molybdenum dioxide completely deplete to metal. Metal will not evaporate at that temperature. Because of this dynamic behavior, we arrive at this conclusion that, summarizing, so in the growth process, you use both the bulk powder, you put only one place. That's why I named it as one pot growth. That means you, in the like in a pressure cooker for making dalma, is very popular for Odisha, you put all these sabji, everything you put dump in the pressure cooker and cook it. At the end it can form something, right? Tasty food or something. I will not get a mixture of or taste of brinjal or aloo or anything, right? But here that same thing, when you apply here, you put all the bulk powder in one place. Now interact with the water vapor. So you can see there is a lot of chemical equation balance you can think about. So what happens? Both water interact with both the molecules. Here in for molybdenum, it form a molybdenum dioxide. For tungsten, it form a tungsten also suboxides. You can see molybdenum, it is directly from molybdenum dioxide. Then molybdenum dioxide again it evaporate. This molybdenum dioxide evaporate and are the substrate that contribute to the growth, that interact with the H2X and form the molybdenum disulfide again. But now here you evaporate from bulk, but at the end we got like your sugarcane juice, and at the end we got sugar. Same thing like that, similar concept. Use bulk powder, but at the end you grow the single crystal of just few is a half a nanometer. But the moment when you use a reducing gas like hydrogen, whatever remaining amount was there, that quickly deplete into molybdenum, right? So that metal will not evaporate at that point. But tungsten oxide, there is a lot of preserves of oxides are there, and hydrogen start leaching out of those oxides, and that contribute to the growth and the pre-existing domain, and that make like the another round of structure, PN, like heterostructure, one material, then you grow another material. And this process, you can see here the chemical reactions, the MO2 that deplete quickly, but the WX2 part, you can, there is a continuous reduction at the same time, they can contribute to the growth as well. And in the moment, you can change the carrier gas from 1 to 2, you can keep switching and you can make this kind of nice sequential heterostructure. And they are all single crystal. And one can control the temperature, the kinetic coefficient, because at higher temperature, you can even make it a bilayer. One layer, then another layer can sequentially grow like that. As I told you, in kind of optical contrast, because their absorption is really 10 to 20%, even if you have a different layer of materials, even for a single layer, the contrast is less. You have a double layer, triple layer. Single layer is 0.6 nanometer, double layer is 1.2 nanometer, 0.3 layer is equal to another 1.8 nanometer, even less than 2. But you can see with the optical microscope, you can see clearly their contrast. And if you zoom it in 100x, you can easily see there is a molybdenum selenide in the middle and tungsten selenide in the outer edge. And if it's a monolayer, it's a bilayer, the contrast is different. And in the scientific world, nobody can trust if you say simply that it is a monolayer and bilayer. But how can you prove that? If you can use the Raman microscope, we can prove that. And the Raman, as I mentioned, Raman is atomic vibration. The modes, E1G or A1G mode, depend upon how they vibrate inside the material. And that's the characteristics of the system materials. So you take a Raman spectra from the whole sample, by like you take a proper pixel, or you can take choose a spot of 500 nanometer by 500 nanometer. You take several spectra from the whole sample like this raster scan, and later on you select a particular peak and map it. Then you can see this, suppose this peak is corresponding to molybdenum selenide, you can see that molybdenum selenide is present only in the middle region. And if you choose the other peak, you can see that tungsten selenide is present in the outer edge. And that if you combine, you take a position map, how the position vary between these, you can how that. This is how we confirm that this is a inner material is made.
Dr. Sahu, can you finish within another 5 minutes?
5 minutes, okay. Fine, because I start late, that's why it's okay. Okay, so this is how we can make heterostructures like in lateral, and we can characterize them, and with the Raman PL and all these things we can make this kind of, you know, that atomically how they are connected. It's a nice cartoon about it. So we can, one good thing about is, so we can transport this kind of material easily. You can see that it's a chemical, you can exfoliate and you can transfer into any ordinary substrates. Okay, and we can atomical things. So I'm not going to skipping these slides. In a device, we can see that these are photosensor, is a PN junction diode. So you shine light, you can see that the current is increasing, so that you know whatever material you are growing, those are mostly made of, they can be useful for the photosensor. Even if we can make up to room temperature, somehow it is missing, I don't know why it is not appearing. We saw that it's a room temperature LED. Okay, I'm skipping these things then. So I will just give, because some of the students are there, they can get some motivation. So I will be the only intelligent species on earth to harness nanotechnology. Of course, it is not, you know about bacteria, they can generate this kind of biopolymer, and once they can form a biofilm, they can communicate. But the point is, how they sense the surface, what is the force involved, how can measure that. These are one of our contribution to make live image in fluorescence, to see the bacterial colonies, how they can maximize their survival by nutrient flow inside it. All these we studied, and using this kind of low dimension nanomaterial, you can see they are nanoware. And what happens when the bacteria can touch a surface, it can bend, right? When it is bending, that is mechanical shifting, and how much it bend, from that one can calculate the how much force it impact. That is nearly calculate up to 20 to 40 nanonewton level force a single bacterial cell can impact on any surface. And we can detail, we characterize with the SEM fluorescent. So live image, you can detect bacterial motion, everything, and we can predict their force, how much force they can act on that. Even we can three-dimensional view, we can make it so that we know how this nanoware arrays and biofilm as a whole, they survive, and for long term to what is their structure in the building block, all things by step we can get information. Okay, so another aspect is, now you know it is a very COVID times, and biosensor are very important. What we work on biosensor is, we have nanowares like semiconductor. Semiconductor are not good for a sensor unless you functionalize, because biomolecule cannot directly attach to semiconductor nanoware. What we can do that we can chemically functionalize the surface particular biomolecule. So you can APTMS or sealant molecule, you can functionalize that, we can be added to another like in particular protein or DNA molecule attached. Remember what the science behind is, this all biomolecule contains some electrical charge. When it is attaching on covalently, what happens, the overall charge transfer in this FET channel will decrease or increase, and that give rise to some information about the what kind of biomolecule is present. How to do the chemical functionalization. Suppose you have some layer of semiconductor, you can make oxide layer OH group, then you can covalently attach APTS, you can confirm by the fluorescent image. So depend on which molecule, then you can do PAG, connect that. Then selectively you can attach different kind of DNA, peptides, proteins. This is how it can serve as a biosensor for all this. You see, although it's a domain of physics, but this can now touch the domain of engineering, chemistry, physics, biology, all kind of topic. So science is becoming truly interdisciplinary. And using that method, we can able to detect protein of femtomolar level by chain detection. Also in the future, it is on demand that if we make this kind of arrays-based device, so that we have many multi-channel, so even if in one chip, one can detect a DNA, another one can detect protein or some virus, so that multiplexable detection is possible if one can make this kind of arrays-based device. These are the future is more on demand that we also make this kind of flexible device so that we can make flexible based electronics things. Okay, so in future, is nanowire is not that flexible like graphene or 2D material. One can use graphene or graphene oxide (TMD) for this kind of ultimate device. So for the student, I'll just give some out of curiosity. One can also learn from nature that there are a lot of inspiration around us, like pick up the lotus leaf and some mosquito eyes. Why they are anti water repellent, like hydrophobic, and how they're surviving, like lizard, how it is moving. That means behind any science on this kind of biological object, there is a science behind it, and it is all about material. If you zoom into the nanoscale level understanding, you can see there is a three-dimensional hierarchical structure exists, and that complexity gives rise to very tremendous amount of opportunity. If one can harvest, then we can really solve many challenging problems of today's world, right? Like one can see here, like see animals, it can, what is inspiring us is, so this particular octopus, you can see it can change its color and it's a three-dimensional shape. That means it can mimic the surrounding, and so that if you can think about developing something, some materials that can change its face, shape, and size or color, something that can be very useful for certain application one can think about. Okay, so the bigger prospect or goal of material science is, if we can at the end find some way to combine various concepts, like you include electronic circuits, and at the same time can do the biodetections or photodetector or sensor, everything we can do as a 3D integration of these various material, and we can do communication, optoelectronic sensing, memory, computing, if we can at all do in a single device. That can be a game changer. This is what we are effectively looking for the future to lead in that direction. You can think about this whole lot of material science is like a child game where you can combine all sorts of materials and expertise from different domains, and you come up with a unique system so that it can really practically solve many challenging issues that we are facing today. Okay, with that, I summarize and conclude my talk, so that we can make this kind of flexible and transparent, high efficient materials, and we can ultimately control their growth at the down to the nanoscale limit, and we can make also tremendous progress in terms of low power electronic devices. And this is are my colleagues, collaborator from US and from Cambridge University, and this is my right now my students, PhD scholars and MTech students, and this we are leading our group, the Quantum Materials and Device Research Laboratory at IIT Kharagpur. And thank you, everyone. Okay, if you have any questions, please go ahead.
Thank you, Dr. Sahu. Now the topic is open for discussions. Any questions?
Okay, it seems I have a question, Dr. Sahu.
Yes, please go ahead.
Yes. So excellent idea that we are putting say tungsten, molybdenum sulfide or sulfide on on any substrate. Say APT architecture, source, drain and gate is there, and we are putting something in there, and you are able to control it in sub nanoscale thickness. Thickness is controlled to down to 0.5 or 0.6 nanometers. That is fine. But my question is that for that to happen uniformly, on the channel, the surface has to be atomically flat. If it is like a regular surface, it has a very uneven surface when we observe in microscopic scale. How do you ensure that the substrate is of any type and then still you achieve without any defect atomic thin?
Okay, is a standard process for semiconductor industry. Always we choose a single crystal of silicon, and be sure that we choose very high quality crystals, and the surface is atomically flat. The roughness is less than the material thickness itself, so that and there is no is physically absorbed. It is not covalently bonding with the substrate.
That's
What
right.
happens? Atoms are going there, forming a nucleation site, and they later on connect in the lateral dimension. They keep growing in all three dimensions. But yes, of course, we cannot grow on every type of substrate. We need single crystals or a high quality substrate. Mostly use silicon substrate, which is few like hundreds of nanometer of thick oxide layer. But that must be done in very precise manner, so that your overall roughness is really less. And this is a standard protocol for the semiconductor industry. You use those kind of substrates.
That's
So
why
I
the
can,
materials are very expensive, you know. So if it
yes,
is
it is
economically
expensive.
managed.
One piece of that substrate of 4 inches is more than 3,000.
Yes. Yes.
And in India, I am struggling now. There is no manufacturing process in it is here. We have to literally buy from everything from outside. Yeah, these are the silicon dioxide substrate. The background is silicon dioxide substrate, and material are grown on that. And not only that, it's a big area also one can grow. Here, you can
Yeah.
see we can make 300 micron, and these are all single crystals.
Okay.
If you
Yeah.
remember, these are single crystals. These are not polycrystal or there is no defect. They are single crystals. Atoms are bonded or grown in a particular crystal direction.
And then how do you control this carrier gas concentration?
Oh, that is we flow with the flow, and we have a mass flow controller. I can go there, that particular slide. So with a mass flow controller, you can control how much flow rate we want to maintain. Those all these things we can control that. It's a mass flow controller.
Okay.
Yeah, by the way, I forgot to mention that because I was in a hurry to finish that, wind up the talk. So these are basically PN junctions.
Yes.
Molybdenum behave like N-type material, tungsten behave like a P-type. That means a simplification is that we are directly growing PN junctions. PN junction diode. We don't need to physically change by chemically modulate that something. We can directly grow PN junction. That's why it is making one step further. Like in the standard semiconductor industry, our mobile chip, everything in our memory device, we have to literally first grow one material and you go there literally and down, go pitch, make it to PN junction. But we can grow directly PN junction here.
Okay. Yeah, it's clear. Yes.
Okay. Any other questions?
Madam.
Any more questions? I think there is no more questions.
Okay.
So let us thank Dr. Sahu for an excellent talk.
Okay. Thank you very much.
Arun, are you there?
Yes, sir.
So, okay.
Please thank the chairperson.
Thank you, madam, for your nice sharing and spend some valuable time with us. Thank you, madam.
Let's go to next technical session. Who is the anchor? Technical session 4.
Yes, sir.
Begin.
Good morning, one and all. Sir, It is my proud privilege to welcome Professor Ajay Patnaik to this 3 days national webinar, OCS REMS 2020, Day 2 Technical Section 4. It is my proud privilege to introduce my teacher, Professor Ajay Kumar Patnaik, to this August gathering. Professor Ajay Kumar Patnaik was born in Puri in 2nd October 1954. He has completed schooling, college from Puri, and successfully has completed MS in Chemistry in 1970, MPhil in 1983, and PhD in 2000 from Utkal University, Bhubaneswar. Professor Patnaik has joined as a lecturer in chemistry in 1984 at DAV College, Koraputu, and is promoted as reader in 1991 and finally promoted as professor in 2009. He served various institutes like DAV College, Koraput, Bhadrak College, Bhadrak Kalikot College, Berhampur, Utkal University, Revensa College, and Revensa University. He has 35 years of teaching experience at the undergraduate and postgraduate level. Professor Patnaik has published 65 research papers in national and international reputed journals. 9 students has completed PhD during his notable guidance, and 1 student got DSc under his able guidance. Currently, 2 students are working PhD under his guidance. His research field are chemical dynamic and drug metal interactions. He was a visiting professor in Department of Chemistry, Utkal University 2014 to 16, and presently continuing as a visiting professor at Revensa University since 2013. Professor Patnaik, associated with various prestigious society such as Indian Science Congress, Indian Academy of Science, Ultrasonic Society of India, Odisha Vigyan Academy, Science Congress, Odisha Chapter, and Odisha Vigyan Odisha Society. He was president of Utkal University Chemist Alumni Association in 2018. He was president of Odisha Chemical Society in 2019. During his tenure, as the president of OCS, annual conference was held in VSCUT, Bulla on December 24, 25, 2009. With these introductions, I, on behalf of OCS REM 2020, welcome to my teacher, Professor Ajay Kumar Patnaik sir, to start the technical section for day 2.
Thank you, Dr. Jali. Is it audible?
Yes, Dr. Patnaik. Go ahead.
Thank you, Dr. Jali, for the introduction. Thanks to the organizer as well as the president of Odisha Chemical Society for giving this opportunity for chair this session. Now, in this session, there are 2 good speakers, Vikas Kumar Jena from IIMT and Debabrata Pradhan from IIT Kharagpur. In the first lecture by Vikas Kumar Jena, the topic is nanostructure materials for energy conversion and storage applications. Vikas Kumar Jena, serving as a principal scientist in Material Division, IIMT Bhubaneswar. Jena has obtained his PhD in chemistry from Department of Chemistry, IIT Kharagpur, under the supervision of C. Ratnaraj. He got the opportunity to work with Professor Bo Chang Group, University of Washington, USA, as postdoctoral fellow. He visited to Technical University Munich, German, as visiting scientist. He has published 70 papers in international journals of high impact factor, 45 papers in national and international conferences, 2 patents and 6 book chapters. His work has received more than 3,600 citations with the H index 31. 5 PhD scholars have awarded degree under his supervision. He has delivered number of invited talks at various institutes and received various awards. Bronze medal, the Chemical Research Society of India in 2021. Young Scientist Award, the National Academy of Science India 2014. Young Scientist Award, by Indian Society for Electroanalytical Chemistry 2013. Young Scientist Award, Odisha Vigyan Academy in 2013. CSIR Young Scientist Award in 2011. Indian Science Congress Young Scientist Award 2009. Odisha Chemical Society Young Scientist Award in 2008. He is an associate editor of Journal of Nanoscience Letters and member of editorial board in International Journal ISRN, Analytical Chemistry, Current Catalysis, and General Chemistry. He has been invited to serve as a lead guest editor for Scientific World Journal. He is a reviewer of many journal papers, particularly new and easy synthetic routes has been developed to produce metal nanoparticles and carbon-based quantum dots, nanodots, graphenes, graphene metals, metal oxide hybrids, which are applied for a lot of promising applications in energy conversion, storage sensitizing, biosensitizing. Dr. Jena work has been highlighted in India Today magazine, September 2013. Now I welcome Dr. Vikas Jena to deliver his talk. The time limit is 40 minutes talk and 5 minutes is for discussion question. Now I request Dr. Jena.
Thank you, Professor Patnaik, for your nice introduction. So very good morning to all of you. So I'm audible to all of you properly?
Yes, perfect.
So thank you so much. On the outset, I must thank to the organizer for providing me this opportunity to deliver a talk with this wonderful session. And special thanks to Professor Swain and all his colleagues for inviting me this platform. So with this, let me start the presentation. So let me share the presentation.
Please make him co-host. Begin. Yes.
So now it is in a slide mode.
Yes.
Okay. So thank you so much. So my topic of presentation is nanostructured materials for energy conversion and storage applications. So as Professor Patnaik mentioned that I'm working as a principal scientist at CSR IMMT in metal chemistry department. This is my group. I thank to all my previous and present students. Those are substantial helping and supporting due to their hard work, the group activities going on. And also the objective of our group activities the development of some bio and electrochemical active materials and to conceptualize those materials to develop some new and bioelectrochemical processes, systems that have some applications like industrial applications and societal applications. So with this group activity, so for this session, it is not moving. Is it moving?
Okay, continue.
Yeah, so, okay. So the outline of my present discussion is, I will discuss about the energy conversion devices, that's fuel cell. So how you have developed some different kind of materials, that's like anode and cathode material for oxygen reduction reaction and methanol oxidation reaction for fuel cell application. Then I'll talk about some energy storage devices, their importance, and how you have tried to develop some new materials for energy storage applications towards supercapacitor. So let us discuss on fuel cells. And all you know what is a fuel cell? Fuel cell is just electrochemical devices that oxidizes fuel at anode and reduces oxygen and cathode to produce the electricity. Why we need some alternate fuel cells? Because all you know why this fuel cell is warrant so much attention, because all you know we are now increasing our importance to develop the energy from renewable energy resources, because all we depend generally from the energy from fossil fuels, and the fossil fuels is running out. That's why you need some alternative fuels and alternative fuel cell devices to get the electricity. And also, if you can see in the environmental point of view, the pollution from using these fossil fuels is very high towards the environmental point of view. And you can see the fuel cell that operate at 60% efficiency, it will emit very less carbon dioxide compared to the engine that uses the fossil fuel cell, and that generate carbon dioxide is very high. And also you can see the energy efficiency of this fossil fuel cell based internal combustion engine and the alternate fuel cell based engines. You can see the efficiency of alternate fuel cell is very high, and also the generation of CO2 on this environmental contaminant is very less. So that's why, and also you can develop some alternative fuels, and that will have giving some development or some captivating power systems that we can carry from one place to another with some proper handle carrying, and which has some kind of disadvantage in case of like fossil fuels. So that is so much parameters are there. That's why now a lot of research is going on how to develop some alternative fuels and alternative fuels like devices to get the energy out of it. So we have seen that so many kind of fuel cells still now it is developed, and a lot of research is going on to develop some alternative fuels and fuel cells. You can see here that solid oxide fuel cells, molten carbonate fuel cells, phosphoric acid based fuel cell, and polymer electrolyte membrane fuel cell where hydrogen is a fuel, and here it works at acidic pH, and direct methanol fuel cell where methanol is a alternative fuel, and alkaline fuel cell where hydrogen is a fuel but it operates in alkaline media. So you can see there is so many fuel cell has already developed, but their operating principle is different. Some of the fuel cell that works at high temperature to get the electricity, and some of the fuel cell that works at a low temperature below 100 degrees Celsius, like our direct methanol fuel cell, polymer electrolyte membrane fuel cell, where hydrogen is a fuel. So now, if you can see the direct, we have given our interest towards direct methanol fuel cell because this fuel cell can operate at a low temperature, and that fuel cell can use as a captivating power generation that we can take this device from one place to another without much care, because it is you can see this is the mechanism how you can design a system where one side will be anode, another methanol, and methanol will get oxidized and it will give the electrons to the cathode side where the air containing oxygen will get reduced so that the electrical circuit will complete and it will generate the electricity. So this is the operating principle of direct methanol fuel cell. There's two compartments. One is anode, another compartment is cathode compartment, and it is separated by a membrane, and that membrane is only allow the proton to pass from this anode side to cathode side without allowing the fuels. So this is the operating principle of direct methanol fuel cell. But whatever the fuel cell you're trying to develop or you are going to design for this commercial applications, but the problem is, so you have to develop some catalyst, and the efficiency of fuel cell only depends, is vital. It's not only other parameters are there where the efficiency depends, but the most major part is your development of catalyst. If you can design a very efficient catalyst that can catalyze this anodic oxidation and cathodic red. Yeah, I'm audible? Yeah, sir, is it okay? Should I continue?
Yes, continue.
Okay. So that's why whatever the you want to do a fuel cell design or develop a fuel cell for commercial aspect, you have to design a good catalyst, because the major part of a fuel cell is your catalyst. And the key challenges for ultimate this commercialization of fuel cell is that how we can develop high efficient catalyst whose activity should be very high and it should be very stable in the operation medium, and also should have a low cost so that we can do some commercialization. And you can see already it is established that this bulk materials is a poor catalyst. When you can tune this catalyst to a nanostructure, nano dimension, then its catalytic activity increases. And this catalytic activity not only increases, you will keep down to nano size. If you can tune further the size to nanostructures, then the catalytic activity increases. Also, you can see tune the shape of the nanocatalyst, the catalytic activity increases, and also the interparticle distance, how you can disperse, how you can distribute the nanoparticle on a catalyst support so that it should not get aggregate, it should not get agglomerate, and the interparticle distance of the nanomaterials should remain in such a way that we can get more high efficient and high catalytic activity. So another thing is catalytic support. So though you can develop some catalyst, we have to develop some catalyst support where you can decorate or you can anchor the catalyst on its surface. You can see, if you can use, if you may not use the support catalyst, so you can mute those who are can request those who are there, they can mute themselves so that it will be properly audible to others.
Dr. Zana, it's okay. I mean, some people are doing it. We are trying to control. Please go ahead.
No problem. Yeah. So yeah, let me continue. No problem.
Yeah.
So that's you understand that the role of support is plays a vital role, because if you can use the catalyst without a catalyst support, you can see the catalyst when you do the synthesis, it will agglomerate, further it will form bigger particles, and the surface area will decrease. Ultimately, the catalytic activity will decrease. And if you use a support, then you can see it will properly disperse and the interparticle distance will remain, and the nano size and the structure will remain, it will not happen. That's why the catalyst support plays a vital role. And with the high surface area material we should need, so that we can accumulate more number of nanocatalysts on its surface, and also it should have good electrical conductivity, because it can turn in the electron transfer process, and should be chemical inert. It should not take part in the chemical reaction, other than it will get corroded and ultimately will hamper the efficiency of the fuel cell. And mostly and generally the carbon-based material is used as a catalyst support, because in case of low temperature fuel cells, because it is good electrical and mechanical properties, and they are really inert in case of alkaline and acidic medium at low temperature. And we can tune the versatility pore and we can the pore distribution, so that the fuels can easily access to the current collector or to the catalyst surface, and the electron transfer tunneling process can be easily takes place. So that's why commonly the carbon-based material is used for fuel cell for low temperature fuel cell development, fuel cell catalyst as a support material. So when we have started our work, we understand, we try to motivate ourselves to develop some low temperature fuel cells using carbon-based material. So we have checked that there is so many different types of carbon-based material till now developed, and their properties already highlighted. We have done a lot of research and we have summarized their property. You can check that for this fuel cell applications, we need to focus on its surface area as well as their electrical conductivity. We have observed that so far the different kind of carbon-based materials developed. You see the graphene, the latest carbon-based material, it has highest surface area, that is around more than 2,500 meters square per gram, and also the electrical conductivity is very high. So that's why we got motivated, so that we can use this graphene as a carbon-based material as a catalyst support to load the catalyst for development of fuel cell applications. So this was our motivation. We tried to use this graphene as a catalyst support. We try to load the metal nanostructures of different size, different shape, and different properties, so that we can enhance towards and we can increase the efficiency towards fuel cell application. We first focus on direct methanol fuel cell, where we have studied their efficiency or activity towards oxidation of methanol, MOR, and oxygen reduction reactions like ORR. So that is the story of what we have motivated to develop the graphene. So then how we can develop the graphene? After the discovery of graphene, there is so many methods has already established, and still so many research is going on to develop some facile and easy methods for development of graphene. But this is a summarized report where it shows there is 6 major approaches has already established, and people are following to develop the graphene by these methods. But you can see if every method they have their own advantage and disadvantage. But based on your application, in which field you are going to use the graphene, so you have to adopt that approach. So you can see some of the approaches that can give some high quality graphene, but you have to compromise with the scalability and yield. And some method you can get more quantity of graphenes, but you have to compromise with the quality. And also in this case of fuel cell applications, we have to develop a huge amount of catalyst, and that's why you have to develop high scalability and high yield of graphenes in this method. So that's why we thought we can use this reduction of graphene oxide method for production of graphene. Because in this case, you can get the scalability is good and also the yield is good, but the purity and the quality will be somehow compromised. But in this case application, still there is conductivity is there and also surface area is quite good, then there is no issue. So then we adopted that reduction of graphene oxide methods for getting the graphene. So here what we did, we have developed two methods. First, we try to develop the graphene oxides from graphite by chemical exfoliation method to get the graphene oxides. Then after successful synthesis of graphene oxide, we put the metal precursors or any metals nanostructures or metal tungsten metal oxide nanostructures of our interest, what we are going to synthesize. Based on that, we can choose their metal precursors. We put with the graphene oxide and we can do the in situ reduction so that the metal, from the metal precursor we get the desired nanostructure, as well as the graphene will get reduced to graphene oxide will get reduced to graphene. So these two methods we adopted. One is graphene oxide synthesis, followed by the in situ reduction of metal precursors and graphene. So this method we followed, and first we tried to synthesize the graphene oxide that I have already mentioned that we have adopted this modified immerse method by chemical exfoliation of graphite powder. So this is the method where we followed that some highly oxidizing reagents we have used to like potassium permanganate, then in presence of some acid. Then we try to generate the nascent oxygens so that the oxygen molecule exfoliate this graphite and functionalize the graphenes to get the graphene oxides. And you can see the graphite powder is black in color. When a graphene oxide synthesized, the color turns to yellowish brown. Then after successful synthesis, we tried to do the characterization. Then we have done the SEM scanning electron microscope, TM, then also atomic force microscope. We understand how much thickness of this graphene oxide is produced. We have observed that around 1 to 3 nanometer kind of graphene oxide can be easily synthesized by these graphene oxide methods. So then after successful synthesis of graphene oxide, we try to develop the some kind of metal nanostructure on its graphene surface. And then first I will discuss about the palladium nanostructure we developed. So before that, let me highlight that for a fuel cell application, till now, the platinum carbon-based catalyst is quite good and its activity and efficiency is very good. But the problem is there is some surface poisoning issue. During the operation, the reaction intermediates will sit on its surface and it will foul it. So that's why you thought that, okay, you can replace platinum with palladium, let us the efficiency remains or not. So we try to develop some palladium-based materials on graphene surface. And this method we have established, this method is called carbon monoxide induced reduction of graphene oxide and palladium. So here carbon monoxide gas is used as a reducing reagent, and this is a gaseous reducing reagent so that the byproduct of a reducing agent will not remain there. Then here we have just tune the synthesis parameter. We could able to synthesize six different kind of electrocatalysts by tuning their shapes and sizes. And also we have compared this electrocatalytic activity towards the commercially available palladium carbon. First we discussed about the methanol oxidation. First we checked about the methanol oxidation reaction. You see this is the control experiment without the methanol. When you add to this catalyst, you can see it is successfully oxidized the methanol in that lower over potential like minus 0.1 volt. And also similarly you can see we have checked with the oxygen reduction reaction. It is efficiently catalyzed the oxygen reduction reaction. That means, and also you have observed that this different catalyst and different size, different shape have different kind of activity, and you can see their activity changes if you can tune their size and tune their shape also. And interestingly, we observed that we have observed how many electron transfer process takes place for oxygen reduction reaction. That we know how to do that. We have some set of rotating disk electrode systems. We utilize that one. So using Cutting-Lewis equation, we could able to calculate the oxygen reduction mechanism, and the number of electrons here we calculate that is around 4, but it's not close to 4 because it remains less than 4 electrons. That means there is something in the formation of hydrogen peroxide that I'm going to discuss in the next slides. So here we are not happy because it is not a complete 4 electron transfer processes. So that's why you thought that okay, if we can make some bimetallic nanostructures so that our problem, our purpose can be solved. So here in this case, we have developed some gold and palladium bimetallic nanostructures, and we have synthesized the bimetallic nanostructure using gold very less percentage, and we have got a flower and a dendritic kind of structures, very tiny nanostructures of gold and bimetallic nanostructure, gold palladium. Then after synthesis, we have done some, then we took with the graphene oxide, then we do the reduction so that this bimetallic nanostructure anchored on the graphene surface. Then this method we have established, we have done a lot of characterization to understand whether the structure is remain on graphene surface or not. So after successful synthesis, we have checked the methanol oxidation reaction. It is really good compared to palladium. And also you have checked the oxygen reduction reaction, and you can observe that we have calculated the oxygen reduction reaction is the number of electron transfer process is 4, is very close to 4. We are happy about that because you see, when the oxygen reduction reaction takes place at cathode, it can follow 2 processes. Either one process, like one step process, it will go over one step 4 electron process where oxygen is directly converted to water. And in another step, it can convert it to 2-step 2 electron process where oxygen will convert to hydrogen peroxide, then hydrogen peroxide will convert to water. But this process, the second one is 2-step 2 electron process is not good, is not acceptable because the hydrogen peroxide will generate, it is oxidizing reagent. So what will happen? It will corrode the electrode surface. So that will foul the electrode surface. That is negative, that is disadvantage. So that's why we should develop some kind of catalyst which should have very highly active, and it can do the oxygen reduction process by one step 4 electron process. That we should follow a 4 electron transfer process so that it is directly converted oxygen to water, which is happened in this case, this bimetallic nanostructure on graphene. That's why this work also highlighted and published in ChemCat Chem and highlighted as a cover page of that journal and also cover profile of that article. So then that was the story. That also I'm not giving much details because we have developed so many kind of different materials for this fuel cell applications. We have checked the efficiency, still a lot of work is going on. So another interesting approach that what I'm going to highlight here, that whatever the material we have developed, this is very good for methanol oxidation as well as oxygen reduction reaction. But the problem you can see, I have already discussed about the direct methanol fuel cell design. You can see one side it is anode, another side is cathode, and it is separated by a proton conducting membrane. But you can see whatever the proton conducting membrane till now developed, this naphthalene is one of the best proton conducting membrane. But the problem is this proton conducting membrane is not that much 100% opaque for this methanol. Sometimes what will happen, some methanol molecules from this anode compartment will cross through this membrane and it will go to the cathode side. What will happen? It will go to the cathode side, it will hamper, it will inhibit the oxygen reduction reactions. So that's why it is called methanol crossover, means the methanol passing from anode side to cathode side, that is a negative impact for the operation of fuel cell, direct methanol fuel cell, and it decreases the efficiency. So that's why a lot of research is going on how we can design some kind of materials, which material, only some material will be very good active for methanol, but that will be not active for oxygen, and the material should be highly active for oxygen and inactive for methanol. If a material will be highly active for oxygen, it will do the oxygen reduction reaction, but if methanol molecules cross over to this side, it is not going to happen to the catalyst because this catalyst will be inactive for methanol, but it's good for oxygen. So that's why if a methanol crosses over from this side to that side, it is not going to give any negative impact. So that's why a lot of research is going on. So to that race, we try to develop some kind of material to avoid this methanol crossover. So here we have developed some manganese-based transition manganese oxide based material as a high tolerant methanol and oxygen catalyst, so that it is tolerant to methanol but is active towards oxygen reduction reaction. But interesting, this step what we followed, and it is very easy to discuss, interesting to discuss that when you have developed some graphene oxides, what happened that side during the synthesis, we have used a potassium permanganate as a oxidizing reagent. Then what happened after synthesis, what we did, we used to wash it out so that we can get a pure graphene oxides. Otherwise we lost that potassium permanganate. So because here we thought, let us trap that potassium permanganate. What we did, we have not washed that one. So after synthesis of graphene oxide, what we did, we did the freeze drying, and we have done the lyophilization, so that we have taken out the waters from its surface, and we have dried that sample so that all the manganese, unused manganese, remained inside and trapped inside the graphene oxide. And after that, we have done the annealing at argon atmosphere, and we have observed very interesting that very hollow like a small nanostructures is developed on graphene surface. So then we have done a lot of characterization to understand what is that. We understand that is the manganese oxide is remain after annealing, that very tiny nanostructures, hollow structures remain on graphene surface. You can see this is a nicely well decorated and well dispersed on graphene surface. So you understand this is a very interesting material developed on graphene, and it is from this synthesis of graphene oxide we adopted this method, and we have done a lot of characterization to understand what kind of structure and is developed. Then what we did, again we try to check this methanol tolerant activity. You can see, you can compare, you see, and this is picture B, you can see this is a platinum carbon which is highly efficient catalyst for methanol oxidation and oxygen reduction reaction. And you can see when you do the oxygen reduction on platinum carbon, this is the oxygen reduction reaction. When you add methanol, what happens? Then this totality is gone, and it is showing the oxidation of methanol. That means totally it inhibit the oxygen reduction reaction. But when you have designed this material, manganese oxide based material, this is the oxygen reduction activity. But when you add methanol, very negligible shift in the potential and current is seen. That means this material is highly tolerant towards methanol, but it is active for oxygen reduction reaction. So that's why this material is we published this work in Journal of Power Sources, and this material is quite good for methanol tolerant activity. So in summary, I just want to compile this materials for fuel cell application, that we have developed different kind of metal based materials on graphene surface, and also we developed some methanol tolerant catalyst, and also we have developed some metal free catalyst. And all you know that question comes, why you are using the metals, noble metals, tungsten metal, they have the cost, whether it can be good for commercial purpose or not. So that's why you try to develop some metal free catalyst by doping some nitrogen, sulfur and carbon. But the thing is, it is not that good, that active like a metal based catalyst, because if you see the cost, then what will happen, you have to compromise with the activity. If you can design some catalyst with low cost, you are going to compromise their activity. So that's why the message is that you can design some kind of material, whether it is cost is being high, but you can recycle that material, you can reuse many times, then it can serve the purpose without compromise the activity. And also in future, we are working on it to understand how this metal nanostructure, tungsten metal oxides is developed on graphene, how this metal nanostructure interacted with the graphene. We are correlating our experimental work with theoretical aspects. So this is something we discussed about that, what we developed for electrocatalyst for fuel cell applications. So next I'm shifting towards the energy storage application, development of materials for energy storage application. So as I have already discussed about fuel cell is the energy conversion device, because when you add the fuel, it stores the energy of that fuel and you give the energy. But the fuel cell, and you can see this is a recon plot showing there is so many energy storage devices are there. The fuel cell is one of the energy storage device that converts fuel to electricity. But when you add the fuel, it stores the energy. But the problem is here, its energy density is high, but power density is low. Suppose we want to get a quick power, we want to quickly discharge that cell so that we can get a very quick power output, but that is not going to give. In this case of capacitor, which is used in fan on a motor to quickly start a fan motor, and we should give a quick discharge. That can only happen through the capacitor. But the problem in capacitor is that it will quickly discharge, it will give a quick power output, but energy will not remain. Within few seconds it gone. Again you have to recharge. So it cannot store. It can store the energy, but it will not give you the energy. Density will be less, but the power density will be very high. But you can see the mother nature. You see, mother nature has developed some creature. You can see this torpedo marmot is a kind of animal is there which can store high energy density, and also you can give you high power output. But till now we have not reached that. So that's why now research is going on how we can design some kind of devices whose property remain in between. It can give you high energy density, as well as when you require more power output, it also give more power output or power density. So that comes the supercapacitor. That is a hybrid kind of device whose properties align in between the high energy storage devices like battery and high power storage devices like capacitors. So a lot of research is going on that. So a lot of scopes is on this activity, because all you know now the solar energy is a lot of trends is going on how we can get the energy from solars and renewable energy. But there should be some logical way we will generate that energy, how we can store. We need a lot of energy storage devices. So in that case, the battery and supercapacitor is going to contribute much on that. So that's why a lot of research is going on to develop different kind of very high efficient energy storage devices like battery and supercapacitor. So this is some mechanism how a supercapacitor works. When it is discharge state, how the charge species is randomly here and there. When it's charged, you see the ion species is separated and adsorbed on the both sides, like cathode and anode sides. So based on their operating principle, the different kind of supercapacitor is developed. One is double layer ADLC behavior capacitors, supercapacitors, that's based on carbon-based material, and some metal oxides, metal-based material. Those are like they can do the charging, discharging through EDLC as well as electron transfer processes. That's called pseudocapacitors. And also you can combine their both activity like double layer and pseudocapacitor to make a hybrid kind of supercapacitor, so that you can increase the energy density as well as power density. And if you can see the features and benefit, if you compare the supercapacitor with the battery, you can see, and they have their own advantage, one disadvantage, one way of supporting to our applications. So you can see for battery, you have to know that much long-term charge and discharge cycles, because supercapacitor is quite better than battery. It can have long-term cycle discharge times, so that if you can develop a supercapacitor, it will last a long time, because the discharging cycle will be very high. And also it's environmental friendly supercapacitor, because you can make this device at in aqueous mediums, and you can no need of some specialized chambers like in the battery we have to do in the inert atmosphere, and you have to use the organic electrolytes. So that's why you can see there is a features and benefits of supercapacitor battery is different, but both have their advantages and they are going to contribute. And you can see so many supercapacitor developed. You can so many electronic gadgets now they have replaced the capacitor with the supercapacitors, and some phone companies and LED drivers they have also developed using supercapacitor as one of the energy storage devices. And some of the highly sophisticated cars has developed where they are making hybrid with battery and supercapacitor, so that they can start the engine quickly and then can run with high speed, very horsepower engines. They are developing where they are making hybrid with supercapacitor and battery, so that they can get quick output as well as quick energy output. So that's a lot of scope is there for development of these supercapacitors. So when we started our work, we got motivated to develop some materials for supercapacitor applications. So when we started our work, we understand there is so much metal-based materials is available. They are supercapacitance properties. The charging and discharging mechanism is good, and they can contribute to more capacitance value, more than 1000 farad per gram. But they have high cost for commercial purpose. But when you have checked the carbon-based material, the carbon-based materials, the supercapacitance property is low, but the cost is less. But when graphene came into picture, we observed that graphene has highest theoretical capacitance value compared to other carbon-based material as 550 farad per gram. But this is very difficult to get that 550 farad per gram, because when you synthesize graphene, what will happen when you separate it out, you make some single layers, and you make it powder and keep in store. Sometimes what will happen, you can see here. So if you synthesize the graphenes, when you store it, you can again restack, and its surface area is decreasing. So this is the case. You can see the schematic I'm showing. When you have synthesized the graphenes, it is exfoliated and the single layers remain. When you store it, again it is restacked, in surface area is decreasing. So that's why this diffusion process and accessibility of ions to the graphene is remain less. That's why you could not able to achieve up to 550 farad per gram. What is the theoretical value? In 2011, one group chemically they have activated the graphene. They could able to reach 166 farad per gram. They have published a paper in Science. So that's why you got motivated how we can increase this the capacitance property of graphene. Here we try to develop some carbon nanodot. So during the synthesis, what we tried to put the carbon nanodot in between the graphene layer, so that when you bring it to its solid form or powder form, so that it will not restack, because the nanodots will remain as a sandwich, so that the charge species diffusion process will be more. So we thought that we can use the carbon nanodot so that it can help to the purpose or not. So that's why what we have done, we have tried to synthesize carbon nanodots by using this hydrothermal method. Then you have synthesized the graphene oxide, you mix both, do the sonegations and do some hydrothermal reduction, so that what happens when during the reduction of graphene oxide, then this the carbon nanodot remain in between the graphene layers, so that it forms sandwich structures, so that it is not decrease the surface area. So after successful synthesis, we have done a lot of characterization. And these are the cyclic voltammetric charge discharge. This is things from here we can able to calculate the how much capacitance property of this material. And also we have done the Reagan plot, the energy density, power density, capacitance properties at different cycles. So that we have done, and then we summarized our data. We summarized how much value we got from this material. And interesting, you see, we got around 196 farad per gram. So that is quite better. In 2011, they published in Science that 166, we could able to reach 196 farad per gram. So that's why this work is published in Journal of Material Chemistry and got a cover page of that article. So, but still we are not happy, because we are only reaching to 196 farad per gram. But for a supercapacitor, you have to generate some material which have the capacitance property should be more than 1000 farad per gram. So then our journey keep on doing the research. Then what we did, we have tried to develop some different way how we can increase the capacitance property of graphene. Here we have developed some method like hydroiodic acid reduction process. So here we have developed some graphene film, because graphene film has some different application. When you develop a wearable or flexible supercapacitor, that time we need some flexible films. So that's purpose we have developed some graphene films, and also we have developed some graphene powder. But this is a different method where we have used hydroiodic acid as a reducing method. So this method, after this successful synthesis, we have done a lot of characterizations, and you have able to understand how much thick of this film is developed. Then now we compare the supercapacitance property of this graphene films and the graphene powders by this approach. You can see the film is, we got around 122 farad per gram, but when you have checked with the powder, we got 233. It was now 196 in our previous report. Here we have increased to 233 farad per gram. But we have compared with the film, and we have provided the mechanism with the powder. So what happened in the case of film, in case of powder, we have seen when you prepare a film, the layers again restack, and the accessibility, it is avoid the accessibility or diffusion of ion processes. But when it is in powder form, you can see the graphenes are randomly oriented, so that the space remain in between the graphene layers, so that the diffusion process is very high. So that's why you could be able to, in the case of powder, we get 233. But both the methods, what the film and powder, they have the application in their own field. This film can be applied in a development of flexible and wearable devices. But the power, yes, is 45. Now it is 36 minutes. Okay. So then we have checked and we have we could able to get up to the value up to 33 farad program. But still we are not happy. This work we published in the Journal of Chemistry. Then what we thought that whatever the method we adopted, we could not able to increase the supercapacitance property of graphene. So then what we did, we tried to make a hybrid with some layered material like molybdenum sulfide. So here the molybdenum sulfide you have developed a hybrid of graphene and molybdenum sulfide. You can see when you synthesize only molybdenum sulfide, then you can see it is getting aggregated and form microstructures. But when you use the graphene oxide and do the synthesis, we see there is layers of MOS2 remain in between the graphene and vice versa. Graphene remains in between the MOS2 so that the layers remain separated and the accessibility of the ions for the supercapacitor property increases. So then after successful synthesis and a lot of characterization, again we summarize the value of this supercapacitance values. We could able to reach out to 318 Faraday per gram. And also you compare our result with some other existing literatures based on this MOS2 based material, but our data shows better than that, and this work we publish in scientific report. But still we are not happy. Further we try to how we can increase this supercapacitance property. Here we try to develop some metal oxides. That was sulfide, some metal oxide based material we developed. Here we develop some vanadium oxides. So after searching the literature, this is the work of my PhD student. So we understand that some vanadium oxide based material, their capacitance property is quite good. So we try to develop this method, and we could be able to synthesize very nano seeds of this vanadium oxides on graphene. You can see from the TM, those layers seed-like structures anchored on the graphene surface. So after synthesis, we have done a lot of characterizations. Then we check the supercapacitance property. So you have this is the CBCD, all the properties, electrochemical properties we have evaluated. We could able to achieve like 737 Faraday per gram. So you are very interesting that when you are switching from graphene, it was when you develop 196 Faraday per gram. So now switching from making hybrid with metal sulfides, metal oxides, we could able to reach about 737 Faraday per gram. So this material is quite interesting. Then we have tried to develop some devices like asymmetric devices. One side graphene, another side is this hybrid material. Then this console we could able to develop, and also we demonstrated this device by powering a LED light. And also we compare our material, the property of material with other existing literatures. So our value is quite good. So that's why this work we publish in Journal of Physical Chemistry. So further, what we again try to develop some other oxide-based material, that's mixed metal oxide material. So here that was only one metal oxide was there. Here we develop nickel cobalt oxide, like two metals, mixed metal oxides we develop, and here you can able to synthesize a very porous nano rod-like structure of nickel cobalt oxide on graphene. And you can see in this synthesis process, you can see this vertically aligned nickel cobalt oxide nanorods remain on graphene surfaces. This method we have developed, and we have done the characterizations how this nickel oxides is grown on the graphene. You can see it is coming, it's just going like vertically and remain distributed nicely on the graphene surface. And these rods are like porous structure and one-dimensional. And this is because of this porous structure, we hope that it will give a good capacitance properties. So what we observed that when we evaluated its properties, and we got a value of 1315 Faraday per gram. So we are very interested, happy that from starting our work from graphene, now we come to making a hybrid material of graphene oxides, a hybrid material of graphene and a mixed metal oxide like nickel cobalt oxide. We could able to reach about 1315 Faraday per gram. So this work we have published in Electrochemical Acta, and also you compare this properties with some existing literatures based on these mixed metals and other carbon-based material. But this graphene and nickel cobalt what we developed is quite high, and 1315 Faraday per gram. So, so also still we are working on, we are developing some new materials for the supercapacitor application. If you can see the summary of our material, we started how we can increase the property of graphene, and we started from 196 Faraday per gram. So now we have reached to 1315 Faraday gram. So then also we have utilized this material to develop some consoles like devices, because we are working in a CSR laboratory which have some industrial applications should be there. We have developed the devices. Now we are in contact with the industry so that we can give this technology to the industry. So now I am going to summarize this storage part of my talk, that we understand there is a lot of materials should be developed, because this energy storage device is quite required, and this high power supercapacitor is very much essential, because we are now generating a lot of electricity through solar. We need some storage mechanism, storage systems. For that, we need very high energy density and power density devices, but the cost should be low and its life should be very high. So that's why whatever the tool material is developed, it is still in the infant stage, what we can say, because still a lot of research is going on, like the battery research, a lot of establishment is going, but the supercapacitor work is still new, and a lot of materials is going on, development is going on, and also there is a lot of effort is going on how to design some high capacity material for this practical application or commercial point of view. So we are on that race, we are working on this. So with this, so now I should thank to my directors, CSR IMMT, supporting me to carry out this work in here in this institute. And also I am I should thank to all my PhD scholars and project scholars, those have substantially and contributed to this group activity, and because of their hard work, we could able to reach up to that level. And also thanks to all my collaborators, those who have supported us and helped us to understand the mechanism and the property of this material to this level. And also thanks to all my some funding supports from CSR, Young Scientists Award projects, MNRE, BRNS, DST, NALCO. They has really supported their fund to carry out this research at CSR IMMT here. And at last, not the least, thank you to all of you for your kind attention and to listen this talk. So thank you so much.
Thank
So
you.
now it's finished. Yeah. So thank you.
Yes, for your nice talk and very interesting talk on the production of fuel from methanol, as well as the power storage battery, high capacitor, which is low cost and long lasting, and a very high power consumption. So high power storage. So this is a very interesting talk, and thank you to Vikas. And any one or two questions, audience may ask.
Okay. May I put a question, Vikas?
Yes, sir. Yes, sir.
Okay. So I often face some difficulty understanding the extreme high values of super capacitance, even close to 1,000. What happens is that in this two-probe measurement that you do, two electrode measurement of cyclovoltammetry study, the amount of material that is deposited on the electrode, the expression C is equal to IT by MV, that mass is there in the denominator, right? So what happens is the amount of active material that is deposited on the electrode is expressed in the denominator of that particular expression. Yes. So when they come down to milligram level, milligram scale, the actual value becomes high. So is there any standard protocol that how much of mass active material should be quoted on the electrode when reporting this kind of data?
Yeah, so you are rightly, sir, you have said rightly, because when you are calculating this supercapacitance properties, specific capacitance, we have to put the material in the denominator, because what happened usually, because how much material you will give that, and that's why what happened, that's why the nanostructures material you have to develop, as well as how you can disperse this nanomaterials, how you are making a slurry out of it, so that you can coat a very thin layer. So that as much thin layer you can put, so that the ions that diffuse can reach to all the materials there in your surface. If you will make a thick slurry, definitely material will be there, but they are not going to contribute the capacitance property, because the diffusion of charge spaces is not reaching to the material. So that's why there is no that kind of protocol hot much layer will be developed, but you have to develop such a thin layer so that your material should be easily access to all the charge spaces or diffuse ion spaces. That should be the idea. So then how you are developing and how you are putting the material on the substrate, that is the major role and playing major role to get the supercapacitance property.
Okay, because I understand all the students, they make slurry and deposit. So in the process of making the slurry so as to make a thin layer, what they do is they dilute this slurry to such an extent that the material coated is less than a milligram. So it comes down to even 0.5, not 1 milligram. So then the expression where you fit in, it shows very high capacitance. So my question was that, is there any international standard that how much minimum should be the mass? I mean, we cannot go below that. You understand my point?
Yeah, I understand. But there is no that much international standard, because you see when micro supercapacitors people are developing, then micromilligrams of samples are there putting. So that's why what the main thing is that whether you are diluting the things, but your film is not homogeneous. Or suppose you are giving less amount of materials, but your film is not homogeneous. When you are calculating the surface area, that's wrong.
Yes.
Because if you calculate the aerial capacitance will be not good, because your material is not properly dispersed. So we have to compare both, as well gravimetric capacitance with respect to your weight of the material, as well as aerial capacitance. So both should be balanced. So that's why you have to prepare in such a way that your film should be uniform, the material should be uniform, the capacitance property, not only gravimetric capacitance, the aerial capacitance should be also high.
Okay, I understand. Okay.
Because I have one question.
Sir, please.
After the supercapacitor is discharged, can you reuse it?
Sir,
or
yeah.
it again?
Because it's a recycling, means a charge discharge cycle is very high, because it is go to 1 lakh times also. Because same device you can charge, again discharge, again charge, again discharge, like 1 lakh times. That's why the supercapacitor, the cycle stability is quite better than battery. But in case of battery, the cycle somehow it will get after some, maybe in battery after 1 year, again it will not charge. But in case of supercapacitor, the cycle stability is very high, so it can be used for a long time.
Yes, that's you have shown it very
Yes,
you have shown it very clearly in one of the slides. The line remains flat over 6,000 cycles. So you have to go to maybe 10,000 cycles to know whether if it is the capacitance retention is 95% over 10,000 cycle, then it is a good material. Then just a query, like, have you patented this high capacitance material? The last one you showed.
Yeah, so we have put the patent under process, because first we have to put the patent, then we have to publish. First we have to file the patent.
That's what I'm asking. I mean, the 1300 something value is pretty high. Yes. Okay.
Thank you, because then we'll invite the second speaker.
So thank you so much, sir, for your opportunity for this talk. Thank you so much.
Let's go to next speaker. Yes.
Now we'll invite the second speaker, Debabrata Pradhan, Associate Professor of Material Science, IIT Kharagpur. He did his PhD from IIT Mumbai, 2 years of postdoctoral research in the Department of Physics and Tomkang University, Taiwan, another 4 years of in the Department of Chemistry, University of Waterford, Canada. He has 140 international journal papers, citation of 5,900, H index 41, I-10 index 111. He has published written one book in Springer Publisher and 2 book chapters, 2 Indian patents. Published papers are in several reputed journals, including OCS Nanoscale, Energy Environment Science, Scientific Reporter, American Chemical Society Applied Matter, Interface, Journal of Physical Chemistry, Langmuir, Journal of Material Chemistry. He is a reviewer of several international journals, including Journal of American Chemical Society, Advanced Material Science, Chemistry, Longmire, OCS Applied Matter and Interface, Journal of Physical Chemistry, Applied Physics Letter, Journal of Material Chemistry. Research interests of Dr. Pradhan are in the field of nanomaterials for the energy generation and storage. 7 scholars have awarded PhD degree under his guidance, and now 15 students are working for their PhD degree. 17 MTech scholars have completed their research work with him. Dr. Pradhan has won several awards. He got Adani Award for Excellence in Teaching and Physical Chemistry and Technical Students of IIT Mumbai, MRSI Medal 2019 by Material Research Society of India, and he is the Excellent Faculty Award 2019 by IIT Kharagpur for outstanding contribution toward the teaching and research and institutional development. Now, I request Dr. Devabrata Pradhan to start his lecture.
Professor Patnaik, Chairman Sir, here is an announcement for me to make. Actually, Dr. Devabrata Pradhan, who is to speak now, he is from IIT Kharagpur. There is a power failure in the institute. So he is maybe heading to his residence or some place where he will get connectivity. So maybe we shall have he will join us after 10 minutes. So within this, this 10 minutes, let us remain engaged with Dr. Vikas Kumar Jana. Are you there, Dr. Vikas? No, but he's there.
Now you tell some coming program in OCS, annual function, anything else.
Okay, I'm a OCS related matter, but we may also continue discussion about that graphene and supercapacitor behavior. Last time also Professor Das was here, and that was an interaction with a professor from Smriti Ranjan from IIT Mumbai or Delhi, I don't remember. But he is also dealing with similar supercapacitor studies. And Professor Das asked the question, what is the effect of the kinds of groups that are attached to graphene, whether electron donating group or electron withdrawing groups? You remember, sir?
Maybe I think I am forgetting things, but anyway, that's all right.
Yes, sir, yes.
I have one point here to ask to Professor Jana regarding it's just something regarding chemistry aspect, not the application side. So he was talking of the 4 electron transfer at a stage. I have never seen such a situation anywhere. At a time, there will be 4 electron transfer because it's a chemical reaction where the electrons are being transferred. So maybe the one of the step is slow electron transfer. Rest others are much faster.
Yes.
Not all the 4 electrons are being transferred at one stage. It's
True.
not like that.
Yes, sir.
That may be one of the situations. And I was thinking of about permanganate being used for graphene oxide formation. Actually, rightly, he has said that it's the impurity of manganese oxide on the surface, which matters was Mn3O4. Others, oxides of manganese, they stays on because once permanganate is used as an oxidizing agent, it is reduced to oxides of manganese. Where they will go? They will stay on the surface. That is what happening. And another thing he pointed out, using hydrogen iodide, HI,
as a
in a
reducer.
process. Yes, use of HI. Again, the same problem might have been there. It did not point out.
Hmm?
Uh, uh,
Acha. Same. Okay.
should I continue?
Yes, sir.
HI.
The speaker has come, but please continue. Let us
Ah.
interesting discussion. Yes.
Now, HI actually when decomposes produces iodine, and if HI is a reducing agent, all right, it will reduce. But iodine, what happens to iodine? Is it not the substance which is going to prepare by UF reduction? Is it not contaminated with some little amount of iodine? Is it creating some problem there?
So actually, the
That
electrode is after coating, it is subjected to a very high temperature in a kind of oven. So in those conditions, probably most of the trapped oxygen is
could be.
goes out.
Could be.
Yes.
Okay.
So, sir, Mr. Chairman.
Hello.
Professor Patnaik.
Hello, sir. This is Vikas. Hello.
Yes, sir.
Yeah, so actually I went to washroom and.
Yeah, please go ahead. We had some snag in getting the next speaker, but now.
So any discussion is there, sir? I am happy to discuss. Or
you can comment something. Yes, then we shall go to the next speaker. Please.
So, actually, I have not listened to anything because just now I came.
Okay. Because sir has asked one question.
Yeah, please, sir.
For 4 electron transfer in one step process.
Yes, actually. Yeah, because this is a simultaneous process, not always.
Yes, that's it. Simultaneously.
Yeah, you are right.
See, there are all at a time that cannot be 4 electron transfer. Only maybe there is only one step which is rate controlling the 4 electron transfer.
Yes, sir.
Others are so fast.
Yes, sir. So you are right. That is there, but when you do the electrochemically, this rate determination.
I understand. Because that is not the point of interest in this connection.
Yes.
But when you talk of 4 electron transfer, one step is there which is slow.
This is a dominating step, yes.
Yeah.
But in other step, where the dominating step is hydrogen peroxide will generate. So once it is generated, again it is converted to water. So generation means that will again corrode the electron surface. So that's why you have to think when there is a 4 electron transfer process, but the dominating process will be more in the 4 electron process. But it is simultaneous. It's not like quickly 4 electron it will give.
Yeah, that's right.
Yes, sir.
Stepwise, definitely.
In sequence, it happens.
Yes, that's right.
Sequence.
Sir,
the products that are generated must be lost.
Must be lost, yeah.
Yes, must be lost.
Time to generate a hydrogen peroxide because quickly the steps will be so quick, the electron transfers, so that only water will generate. So that was the.
That's right.
Sir, anything
and
else?
Your iron didn't create any problem in use of HI as a reducing agent?
Yes, sir. Actually, that was a really nice question because when you do the reduction of the hydroiodic acid, iodine remains on the surface also. After washing, you have washed with some different dilute HCl, try to washing it out, but still some ions remains on the graphene surface. But when you have done the supercapacitance property, you checked, but it is supporting, not it is a disadvantage because it has some pseudo capacitive behavior, it is helping. So
that's what I wanted to know. Yeah. But Dr. Samal said iodine will drive away iodine from the surface.
You put it in the oven and
so whatever, sir, we have done also, still some iodide ions even trap inside because it will not 100% go. But we observe that it is not a disadvantage. They are contributing. That's somehow contributing. In that paper, we have done the XPS, we observed that iodide ions are even.
Next speaker has joined.
Okay. Thank you very much.
Devrata Pradhan from IIT Kharagpur. I invite you to start your lecture. Devrata, have you joined?
He's there, no? His slides are on, means he's there. Dr. Pradhan, are you there? Say, but unmute Karinai. Please make a call to him. Begin.
Yes, sir.
Hello, good afternoon. It was muted.
Yes, yes.
Okay, let me share the slides. Do you see my slides?
Yes.
Yes,
Okay,
yes.
good. Thank you very much. Okay, already we are late. Let me quickly start. The topic that I am going to talk here is the heterostructure for hydrogen generation. In the sense that, as we know, that hydrogen is one form of energy. It is a chemical energy. It can be generated by different process, but the focus will be on how to generate hydrogen using heterostructure, particularly semiconductor heterostructure or metal semiconductor heterostructure from water splitting reactions. We have many form of energy. All the universe is composed of nothing but energy, but scientific community has to explore the way to generate energy from these resources available. Some of these resources are renewable, some of these resources are non-renewable. At present, 70 to 80% of the energy consumption occurs from the non-renewable resources, but the energy crisis and other issues such as global temperature pushing forward the scientific community to use renewable energy. The Paris Accord climate issue becoming the hot issue of the world community. And in that sense, we have different renewable sources such as water, air, sunlight. All these are quite renewable, and people have been using those renewable resources for energy, but those need to increase. In that sense, solar energy is one of the most abundantly available renewable sources, which can be converted to the chemical energy using photochemical reactors. You can use that chemical energy such as hydrogen using the fuel cell batteries to electrical energy. As Professor Dr. Jena was speaking just now, how fuel cell can be utilized for energy purpose. And in that sense, here fuel cells battery could perform a part of this problem to solve this problem. Again, then we have solar cells. Directly, we can convert solar energy to the electrical energy using solar cell. Our group mostly focus on this research, particularly developing the materials for this type of energy conversion. We have many other forms of energy, certainly, no doubt, and all these forms of energy can be converted from one form to another form using certain kind of systems, device, and all those system and device needs material, and for that, the material scientist comes into picture. There is nothing created, nothing is destroyed. It is just a form of one form to another form, as Lavoisier, French scientist, told once. In addition to the energy generation or energy conversion, we have energy storage device will play a crucial role, which discussion was going on in the previous lecture quite a lot. We also work on that. Just briefly, what we do in our group is that we work on synthesis of the nanomaterial using solution chemistry method, the chemistry route, and utilize those nanomaterial for different purpose, including environmental remediation, catalyst for fuel cells, photocatalyst for hydrogen generation, and electrode for supercapacitor. In this research, we work particularly, for example, safe control synthesis. We work on different oxides, chalcogenides, mixed oxide materials, synthesize many different materials we utilize for different application. We utilize for photocatalytic hydrogen generation. That is what the topic of research, the topic of my presentation here, that we will come to here. Also, we also work on catalyst for different kind of fuel cells, different materials we synthesize used for. We have studied so far hydrogen fuel cell, alcohol fuel cell, and different type of reactions such as hydrogen evolution reaction, OER and OR, all kind of things we do. In addition to that, many of these materials that we synthesize are suitable for supercapacitor, therefore, and we have a lot of facility available for electrochemical study. Therefore, we also do some supercapacitor studies. So these are the research that we do in our group briefly. But as I have given several talks at BSSUT in the past on some of these topics, today I will be very focused to only one topic, that is the hydrogen generation using heterostructures. or the couple of papers, work from the couple of papers that has published recently. I will give 3 examples, particularly semiconductor heterostructures, and a metal semiconductor heterostructure, and another for same material, TiO2, but with 2 different phases forming heterostructures. So these are the 3 different materials on which I will present. As we know, hydrogen is a form of chemical energy, and it is the lightest most in the periodic table, and it has a very high energy caloric value. The high heating value, nothing but the gross calorific value or gross energy. That is nothing but defined as the amount of the heat released when a particular amount or specific quantity is combusted and the products goes to a high temperature and return to 25 degrees centigrade. It begins with initially with 25 degrees centigrade and then come back to 25 degrees centigrade, and that much of heat is released is called high heating value. In the low heating value is nothing but it will when it combusted, it will go to high temperature, and then when it comes up to 150 degrees centigrade, and that is what defined as a low heating value. In both cases, hydrogen has much higher that means energy value in comparison to all other type of fuels available. In all other type of fuels, we have certainly carbon, and therefore the weight is certainly higher compared to the hydrogen. And as if you are aware of the research going on, already there is hydrogen powered vehicles, quite a lot of vehicles on the car, buses, etc. But now the trains have also come. In particular, Germany have developed a passenger train, and it has been running since 2018. And this train is now has been introduced in Austria, Netherlands, these type of countries.
Also der Befüllprozess selber ist genauso leicht wie beim Diesel. Es wird eine Befüllkupplung angeschlossen, verbunden mit dem Fahrzeug. Dann wird an der Anlage der Prozess gestartet und nach 15 Minuten ist der Befüllprozess abgeschlossen.
Ja, sieht alles schöner aus. Es war vielleicht ein bisschen wackeliger als die älteren Modelle, aber
so it gives the importance of the hydrogen, no way. That as I said, that this type of train has been running in last 2 years in Germany, and also it has been started running in Austria in last year. And slowly it will pick up for the future. And just a simple example of fuel cell, it has been also shown previous lecture, how hydrogen can be oxidized at anode in presence of a catalyst, and mostly we use platinum catalyst because of its high performance. And Dr. Zena has given quite a lot of information about how that oxidation reduction, and again in the right side in the cathode we have reduction reaction. Oxygen get reduced, oxygen reduction reaction occurs at cathode. And problem with platinum is certainly, as being told, that poisoning, catalyst poisoning, and certainly platinum is also expensive. Other issues are also there, fuel crossover. These things are there with catalyst. So people have been in last 10 years working quite a lot with this type of oxygen reduction, oxygen evolution, this type of catalyst to find an alternative to platinum that could also serve the purpose. As far as the hydrogen production concerned, we have at present mostly industrially we are doing the stream reforming to generate maximum percentage of hydrogen industrially, which is energy consuming. This reaction goes on at a high temperature of 700 to 800, 700, 900 degrees centigrade, and it also produces greenhouse gases, carbon monoxide, carbon dioxides. And therefore, it is not certainly advisable to continue, and we have to look for other options. And there are many other options from which hydrogen can be generated. There are some bioprocess. There is hydrogen can be generated from different type of biomass, called gasification, but they also produce some kind of, we also use that non-renewable resources. But among these, something which is more appears to be more attractive or appealing is that water electrolysis, where electrolysis should occur from the energy coming from the renewable resources. Electrolysis of the water can certainly be done with renewable energy, such as electricity coming from solar photovoltaic or coming from the hydro power. But again, that is not very attractive in the sense that, again, we are using some energy that is already there, which we can directly utilize. But it has certain advantage that you can use it for fuel cell. But what two other processes, that is photocatalytic water splitting and photoelectrocatalytic water splitting, are more appealing in the sense that you directly use sunlight to split the water, and water is abundant, and sunlight is abundant. And then use it for producing hydrogen, and that hydrogen you can use for electricity generation using the fuel cell. So that is what I will discuss. Electrolysis, as everyone knows, it is energy consuming process needing 1.23 volt. Actually, in practical, we need 1.8 to 1.9 volt. And in this process, catalyst is used, which helps to break down the water molecules, produce hydrogen. And as per the catalyst is concerned, we have the catalyst, the important properties of the catalyst is like it should be highly abundant and inexpensive. In that sense, platinum do not fulfill the criteria. It should have a small over potential. So potential required to increase the current density 10 times. And we should have a small Capel slope, high exchange current density and mass activity. Exchange current density is the current that produced at without bias. So all these important requirements is there to have a best catalyst. As per the literature, as per the previous studies, platinum fulfill most of the criteria except that it is less abundant and it is inexpensive. Certainly it is expensive. Therefore, it do not fall into the category of that. That research has also been done towards increasing the performance of the platinum catalyst by doing the nanostructuring, forming alloys with non-noble metals, depositing sub-nanometer platinum on the suitable substrate. That is what the previous talks have also emphasized, how the platinum or palladium, this type of noble metal, can be deposited on sub-nanometer size or suitable substrate to reduce their uses, the quantity of the uses, to get performance. But my talk here is on the photocatalytic water splitting and photoelectrochemical water splitting. Just for those undergraduate students who are here or who have no much idea about that, it is just simply you take a semiconductor photocatalyst. Semiconductor photocatalyst is semiconductor, as you know, it has a finite band gap. Metals, we do not have a band gap, where valence band and conduction band overlap each other. On the other hand, insulator, where valence band and conduction band are far away from each other. On the other hand, semiconductor are the materials which have their valence band and conduction band close to each other with a gap of approximately up to 3 electron volts or up to 4 electron volts. If it is a little higher, above 3 electron volts, we say it is a wide band gap semiconductor. If it is less than 1, we say it is narrow band gap semiconductor. So a semiconductor, it is not only that semiconductor has also different other characteristics. So in this particular type of studies, semiconductor photocatalysts are used to split the water molecule. And once you put it into the water or as aqueous solution, and then shine with light, then depending upon the band gap, if the incident energy or the sunlight energy is greater than the band gap of the semiconductor material, then electron holes generation occurs. Like if the energy of the incident ray is greater than the band gap energy, then electrons will go from the valence band to the conduction band, producing a hole in the valence band and the free electrons in the conduction band. And those electron and holes can be used for the reduction and oxidation reduction respectively. Hole will do oxidation reaction and electrons will do reduction reaction. So now these hole, and first is the generation of electron holes, that is the light harvesting process. It should absorb the light and produce as much as electron hole possible. Then these electron holes should migrate to different surface sites instead of getting recombined, so that they can do the desired reaction. If they produce and get recombined, it becomes no use to us. So they should goes towards other direction and reach to the surface, and the all heterogeneous catalysis reaction occurs at the surface between the solid and liquid interface. So oxidation reduction occurs, charge separation and migration to the surface sites is the second important criteria, and then the reaction to produce hydrogen or oxygen. So you put the catalyst particle into the aqueous solution and shine the light and make sure that there is electron hole is produced and they are separated and doing the oxidation reduction reaction. Then you generate hydrogen or oxygen. So now these hydrogen oxygen can be separated by suitable device or a photoreactor. You can use a polymeric membrane or wall to transport or to pass this hydrogen gas out from a different chamber and oxygen different chamber, so that you can collect hydrogen oxygen separately while performing the reaction, while doing the reactions. So this can be done to produce hydrogen and oxygen. The advantage of this type of photocatalytic water splitting is that it is a simple process. You can just put the powder photocatalyst into the water and disperse it and do the reaction. But disadvantage is that you can have a backward reaction. Water, hydrogen and oxygen can recombine to produce water. And second thing is that additional bias voltage cannot be applied to facilitate water splitting. As we know that water splitting reactions occur practically at a voltage of 1.8 to 1.9 volt. So if the semiconductor is not good enough or cannot produce that much of voltage, you cannot additionally put a voltage to do the or facilitate the water splitting reaction. And the third thing is that additional cost for hydrogen oxygen separation. This has to be done in a photocatalytic water splitting. On the other hand, in a photoelectrochemical water splitting reaction, you can have a semiconductor, and when sunlight falls on it, it produces hydrogen holes and electrons, and your holes will react with water, produce half oxygen and H plus ions at the water at the working electrode, and there's a hydrogen ion will go to the counter electrodes. When oxidation occurs, that means it will produce H plus ions, and also it does that electrons will also transfer from a working electrode to the counter electrode, and those electrons can be utilized at the counter electrons to produce hydrogen from H plus ions. So first you will generate electron holes at the working electrode, which is nothing but is a photoanode. Let's say, for example, photoanode. Then oxidation of water producing holes at the photoanode, and it will produce oxygen, and then transport of H plus ions and electrons produced at the photoanodes to the cathode. So hydrogen ion will come through the electrolytes, and electrons will come through the outer circuit, and that would do the reduction reaction at the cathode. So these oxygen and hydrogen are produced at different places, different electrodes. Therefore, further separation is not necessary. And additional things is that it is an electrochemical process. You can apply additional bias voltage that you need to the working electrode in case the semiconductor is not sufficient enough to produce the voltage needed for water oxidation. And once hydrogen is produced, you can store it and then use for fuel cell. So advantage is here that you use external bias to drive the reaction in case it is not sufficient. And one important requirement here is that in electrochemical process, the electrode has to be conducting, then only you can apply the bias, otherwise you cannot apply the bias. And no backward reaction of water splitting, no backward reaction, because hydrogen is forming at one place, counter electrode, oxygen is forming at anode, at working electrodes, they get generated at different place. So no backward reaction occurs. So and second thing is that you do not have additional cost to separate them. Disadvantage is that all electrochemical process on the surface, so you need to have separate coating process. So you have to have a conducting substrate on which you can we can coat the materials or photocatalyst material. And as compared to the powder catalyst, it cannot have a very high surface area, because once you coat on the surface area will decrease unless and until it is very porous kind of things. But still, compared to the powder, it will be less. Surface area will be less. So the basic requirements is that suitable band gap, certainly greater than 1.23, but again 1.23 is not enough. You need little higher band gap, preferably around 2, more than 2. Must have a low charge recombination, must be stable, corrosion resistant, because you are doing in the aqueous solution, and should be high performance. And for doing the storage, you need to have you need to connect the cell with a gas chromatograph or volumetric process to measure. Then you can have a solar simulator or any kind of lamp to do this work. And you need a potential start for photoelectrochemical process, because you have to apply the bias. Properties of the good photocatalyst is the band gap should be 2.4 to around 3.2. The valence band should be lower than the oxygen oxidation potential. That is, it should be lower than 1.23. And conduction band should be higher than hydrogen reduction potential, that is above 0 volt on the standard hydrogen reduction potential. And generation of the water from molecular oxygen and hydrogen must be reduced, and electron transport or electron hole transport to the surface is certain, must be needed. So here are the semiconductors that have a potential for water splitting. As you see, many of the these semiconductors have their reduction potential above 0. That means below the 0 in the negative side versus normal hydrogen electrodes. And many of those are having the oxidation potential, which is greater than 1.23, which is the oxidation potential for water. So these factors, once they fulfill, then that can be utilized for water splitting reaction. But again, you cannot use very large band gap material because it will not absorb the solar light, visible portion of the solar light. We want semiconductor which can absorb more amount of the sunlight, that is what in the visible region. So the band gap is supposed to be falling in the region of green region where we have maximum intensity in the electromagnetic radiation of the visible light. So those factors has to be considered. As I said, the corrosion resistant to be there. So all these factors to be there to consider. So coming to the work, we have done with TiO2, and I had presented before also about other type of hydrogen generation process, but here just giving an example of heterostructure. One of the heterostructure is TiO2 copper sulfide. TiO2 is a large band gap material, therefore it needs UV light. It has a band gap of 3.2 to 3.3. But on the other hand, copper sulfide band gap is small. It is less than 2.5 electron volts. So we thought of making this heterostructure so that to increase the absorption properties of the heterostructure, copper sulfide can absorb more visible light. And then we prepared this TiO2 in the form of nanospindle. That means it is a type of elliptical materials, elliptical shape. And the copper sulfide was synthesized at by again solution-based method at 70 degree. It is a flake type of structure. Then we formed the composite or heterostructure. It was synthesized again by a solvothermal process by adding different amount of the copper sulfide to the solution to produce a heterostructure of COS to TiO2. And the composite were designated as CTR, where R is the mole ratio of COS to TiO2. Depending on how much COS copper sulfide was added to the TiO2, the mole ratio was assigned. And here you see the transmission TEM image of them as they are crystalline in nature. TiO2 is in the form of anatides, and copper sulfide is also crystalline. The flakes are crystalline, and when we form the composites, as you see that these flakes and TiO2 are well connected to each other, and X-ray diffraction also gives confirmation regarding their presence, both TiO2 and COS in the crystalline form. Then we did the photocatalytic H2 generation, hydrogen generation, simple photocatalytic by dispersing this powder catalyst inside the aqueous solution. And the production that was studied with different catalysts, as we see here. We have found that a particular mole ratio of the copper sulfide to TiO2, which is CT 0.4, subscript 0.4, gives the highest photocatalytic hydrogen generation performance. With simple direct only TiO2 is low. Again, only COS is low. We compare with the P25, that is a Degussa titanium dioxide, which is the reference standard sample, which is certainly low. In the left side plot, you see the hydrogen evolution rate versus irradiation time and different photocatalyst. In the right side, we have also done with using the only visible light by putting a cutoff filter. The cutoff filter will allow the radiation which will only allow the electromagnetic radiation which is greater than 420 nanometer wavelength. And that's only taking the visible light portion. Certainly the hydrogen evolution rate decreases because we just remove the UV part or the UV part of the sunlight, which was utilized for producing electron holes with TiO2. The second confirmation was done with that best performing CT 0.4 composite with TiO2. This was done with an electrochemical setup. As you see here, as we turn on the light, the photocurrent shoots up because of the photoreaction producing the electron holes, and therefore the photocurrent or the current was measured in the outer circuit. More electrons are generated means you can measure the higher photocurrent, and as soon as we switch off the light, the current goes down. So it is a very sharp up and down, because as soon as you allow the light to fall on the sample, electron holes will generate, and then electrons and holes can be separated to produce those, to do the reactions. In the right side, you will see impedance spectra or electrochemical impedance spectra that was used to measure the charge transfer resistance between the electrolytes and electrodes. In presence of light, we have more electron hole generation, so and in addition to that, charge transfer resistance was found to be smaller or lower as compared to in the dark, under the dark. In addition to that, the composites gave a smaller charge transfer resistance than the pure sample. We have studied the optical properties. Optical properties matches with the literature, like titanium dioxide has a band gap of 3.2 to 3.3. That is what you see in case of pure TiO2. The red color graph in the left side observance, and in the middle you have a tau plot, where the band gap was estimated to be 3.2 to 3.3. And as we made the composites, the copper sulfide goes into the system, the band gap started to decrease, and for copper sulfide it is less than 2.5, around 2.4 electron volt, which is match with the literature also. In the right side, you see a photoluminescence spectra. Photoluminescence spectra, as you see the red color curve, which is for TiO2. TiO2 gives the maximum luminescence, means maximum recombination is occurring with TiO2. That means charge carriers are not well separated with TiO2. But what we can see, the smallest intensity or lowest intensity is found with, again, CT0.4, which is the best catalyst. Smallest or low photoluminescence intensity indicates that there is less recombination. Therefore, the luminescence intensity is very low for this particular composite sample. And this is the reason why this composite sample CT0.4 gave the maximum hydrogen generation ability. But if we look at the observance, as per the observance is concerned, then we have this blue curve CT0.5, where the copper sulfide percentage is more, that absorbs more light. It absorbs more light because it has more copper sulfide, and copper sulfide has a band gap 2.4. It can absorb more electromagnetic radiation, sunlight, as compared to all other samples. But even though it is absorbing more amount of the sunlight and producing more electron hole pairs, but they are not well separated, and there is recombination is more in that sample, even though copper sulfide is more. So therefore, they do not give higher hydrogen generation performance. So an optimum value of 2 is required. If we look at the energy band diagram and the mechanism of the hydrogen generation process, what we see that in the heterostructure, we have both copper sulfide and TiO2. If we just take TiO2, the electron holes generation will occur and they will recombine. If we take only CuS, again electron hole generation will occur and they will recombine. There is no charge, there is no electron hole separation. But when these two materials comes together, then electrons from the copper sulfide, because its conduction band position or Fermi level position, the conduction band position is higher, so electron will transfer from the copper sulfide to the TiO2. On the other hand, the holes will transfer in opposite direction, making electron and holes are well separated. Electron and holes are well separated, and therefore giving better performance in the hydrogen generation. But if we see here, the hydrogen generation is occurring on the TiO2 surface, not on the copper sulfide surface. Copper sulfide is also again undergoes photocorrosion. We have tested with photocorrosion. Photocorrosion was less when it forms the composite. But most important point to note it here, that we have hydrogen generation on the TiO2 surface. Now, if we take more amount of copper sulfide, and this copper sulfide will CuS will completely cover TiO2. At a higher, larger quantity of the copper sulfide, when the mole ratio of the copper sulfide was higher, it completely covers TiO2. As it completely covers the TiO2, then it has no exposed surface, no exposed place where this hydrogen generation will occur. Even though electrons will come to the surface, there it will find copper sulfide, and it will not find an water solution electrolytes. Therefore, no reduction reaction could occur to produce hydrogen. And therefore, it is important to have an optimum ratio at which you have copper sulfide TiO2 are in a balanced manner, where enough exposed sites available on the TiO2 to do the reduction reaction. At the same time, copper sulfide contributing towards absorption of light, and that's creating more number of electron hole pairs. So what we have seen here in this example is both copper sulfide and TiO2 are semiconductor. TiO2 is a wide bandgap semiconductor, and copper sulfide is just a semiconductor. By forming heterocomposites with a optimized ratio, we can enhance the hydrogen generation ability, and which was around this CT 0.4 with an optimum ratio of the copper sulfide to TiO2 gives the best performance, which was confirmed or by the photoluminescence certain photocoherent measurements, establishing the efficient charge separation and less recombination. Coming to the next example is there are other ways to also improve, which I am not talking here. The safe control or controlling exposed facet synthesis, etc. I had presented before at BSSUD. So let's finish that. Let's go to next one. Metal semiconductor heterojunction. In a metal semiconductor heterostructure, we have chosen a semiconductor GC3N4, which is a polymeric type of materials. This is new materials. Students are interested to work on it, and they work on it. Sometimes you say it or not, they would like to do. I say, okay, go ahead. So they have prepared GC3N4, which is a type of composite, and they put different type of this noble metal catalyst, gold, palladium, AUPD. Actually, they found in the literature that people have done work on the single type of metal to decorate on GC3N4, and then they thought to form this type of alloy particle of metal particle, and to study what the performance. That is what their objective was. And they have done the work taking a different amount of the gold and palladium precursor and doing the reaction and producing a different ratio of the gold and palladium and alloy. So as you see here, the composition of alloy particle, in one case only gold was decorated on GC3N4, and another cases palladium was simply decorated on GC3N4. But in other three cases, we have gold palladium with different ratios. In one case around 60-40%, one case 50-50%, and another case 38-61%. So this was the result, and this was the initial concentration on which it was taken, different type of quantity. The reaction was done simply by at a low temperature solution-based method process. And in another work, the same students, what he did, that another combination he had taken, gold, platinum, previous cases palladium, it was platinum these cases, and then gold, platinum alloy catalyst was taken. And then a different precursor was taken. Again, similar type of reaction was done. It was done in a hydrothermal process at 200 degree 48 hours. And we have synthesized, in addition to the gold, platinum on GC3N4, we have different type of these alloy with different composition, different percentage of gold, platinum by varying their concentration. Here is the morphology of the sample. What you exactly see in the top, this is the just scanning electron microscope photographs. As you see, the bright dots are nothing but these metal particle, either gold or palladium, or gold palladium alloy. Certainly palladium particles are quite small in the size less than 5 nanometers, and in the alloy cases it is even it is also quite small, and they are well decorated on GC3N4. These globular particles are in the background are GC3N4. The bright dots are metal particles, and the lower part you see the TEM image, and TEM image clearly confirming that how well decorated these particles are on the GC3N4. They are detailed studies also performed, and in another study like gold platinum cases, gold and platinum and gold platinum alloy cases, you also see here the TEM image. These particles are well decorated on the GC3N4, and they were detailed characterized by different techniques. The crystal structure, the formation of the alloy was confirmed from the X-ray diffraction. This is what more important to confirm that how the alloy formation is occurring. In the right side part, as you see how the peak shifting is occurring for these samples. For initially it was a gold sample, the gold despacing, and the last one is palladium. The B1 is palladium, red color one. So as you keep on forming alloy, as you see how the peak shifting is occurring, confirming that there is alloy formation. In case of this. Similarly, also the X-ray diffraction pattern diffraction studies are utilized to confirm that there is formation of alloy with gold platinum in addition to the TEM studies. So this study confirmed that formation of the alloy and also simple particle. We have done also XPS, and that also confirms the formation of this alloy comparing with the peer sample. I'm not going to details about these studies. These are important studies, and to confirm this that what type of sample is forming. Optical properties are also studied, particularly as you see in the left side, when the gold only gold was there on GC3 and 4. Gold particle was very small size. Therefore you see the surface plasmon resonance effect due to its SPR effect of the gold particle. But once they form the alloy particle, those SPR effect is not strong, but absorption was found to be little higher in the visible range compared to only GC3 and 4. And then band gap, etc., was calculated. There from the band gap and XPS and other kind of studies, we have estimated their conduction band position, valence band position, which are found to be in the range required for the water splitting reaction. As you see, the conduction band position are minus 1.23, which is above 0, and the valence band position are below 1.23, which is like these are all suitable for the water splitting reaction. Then we studied the photocatalytic H2 generation study with this setup of the catalyst. What you see in that in both cases, both set, like in one cases gold palladium, in other cases gold platinum. In both cases, when the alloy particle was decorated on the GC3 and 4, they give the better performance. In the gold palladium cases, when the ratio of the gold percentage was 60% and palladium was 40%, that give the best performance. On the other hand, in the setup of gold platinum, it was the gold 50% gives the best performance. But most important point to note here that when the alloy decorated particle, nanoparticles on the semiconductor surface given better performance as compared to just either on the single metal particle, either gold or platinum. So detailed hydrogen generation experiment through photocatalytic process was carried out and also there are different cyclic studies were performed and they were found to be quite stable for at least 20 cycles that didn't carried out. In this case, 4 cycles are shown. The mechanism here is that again the same thing, the electron hole separation is be higher, but more important, as I say, that why gold platinum or gold palladium alloy particle given the better performance, it is because of their adsorption ability to the water. When a single type of particle was taken, because hydrogen, this water molecule has to be coming to the surface of this catalyst particle at which reduction will occur. So their adsorption ability, their electronic structure of the surface of this nanoparticle are relatively better or comparatively more suitable for water adsorption and then doing the reduction reaction. And that is why this alloy particle given better performance in heterostructure as compared to when we take the single particle. So there are previously a lot of studies were done on as I said, that on either taking gold particle or palladium particle or platinum particle. There were not many studies on this type of alloy for this kind of measurements. So what we have confirmed that if we can an optimum value of each metals in the alloy, they can improve the performance of water splitting reaction. Those things again been confirmed, that means electron hole separation was confirmed for photocurrent measurements and photoluminescence measurement, and they were quite matched. Like when the luminescence is low, that means the combination is low, those catalysts given the better performance in the hydrogen generation. So as theoretically know that we need to certainly improve their charge carrier separation inside the materials to get the better performance. So in this conclusion, what you again see that heterostructure certainly improve the light absorption and also charge separation ability, producing the higher performance. Alloy particle with an optimum ratio was found to be superior compared to taking single metal. Coming to third part, where a single material was taken to study the hydrogen generation performance, and the single material was taken as a TiO2, titanium oxide, which is a very well-known photocatalyst, widely used, and a couple of my students have done PhD with these same materials, and quite a lot of work done on the TiO2. And in this particular study, we have done by controlling the phase of the TiO2. TiO2 exists in many phases, such as anatase, rutile, brochite, etc. In this particular study, by varying the reaction medium or varying the solution, reaction medium, one can synthesize or one can synthesize a particular phase of the TiO2 in the solution-based method. Like there are reports like if you increase to high temperature, certainly you can form rutile phase or different type of phases. But doing the reaction at temperature below 200 degrees centigrade and in the solution process, controlling the phases is quite interesting. So though our initial objective was to synthesize with different phases, and we ended up with finding their morphology also a little bit of changed. Like when we synthesized only anatase, which is assigned as A1, which was synthesized with acetic acid of 16 ml, water 4 ml, without taking acid. Here no acid was taken, and it produced 100% anatase TiO2 with a shape of nanoparticle. As we keep on increasing the acid content, HCl was increased to 1 ml in a 20 ml solution, and water was reduced to 3 ml. Similarly, as we keep on increasing the HCl, we reduce the water, and as we keep on increasing the HCl content in the solution, we found that not only the rutile phase starts evolving, but also the morphology evolved from nanoparticle to origin shape sphere composed of nanorods. Particularly the acidic medium facilitated the formation of not only rutile phase but also the rutile phase, but also the nanorod shape or one-dimensional structure. We have also measured their surface area because that is also one of the important criteria for heterocatalysis reaction. That means heterocatalysis. And then these are the XRD. From XRD, we confirm there are presence like either pure anatase phase or pure rutile phases or mixed phases. So this is confirmed, and the morphology is concerned from the SEM. As you see, when we have only anatase, then we have nanoparticle shape. And as we keep on increasing the acid content, exclusively here it is HCl content, like 1 ml, 2 ml, 3 ml, this morphology going from particles to spheres, but these spheres are actually made up of nanorods as a origin shape. So they are highly compact nanorods. So these nanorods are very small small in diameter. And as you see in the TM image, in the left side, it was a nanoparticles of size less than 10 nanometer. And then the nanoparticles are evolved as we increase the acid contents. These nanoparticles comes together as you see in the insert of the figure C. The blue particle or schematic diagram in the blue color particles are anatase, and they are attached. They are started to becoming that aligned and getting connected to each other with another phase coming in between rutile. So we have done measurements through high resolution TM, finding these initial particles are this spherical, almost spherical type, not very spherical type, but these particles are anatase. And in the side, we are finding the rutile, the d-spacing or the lattice parameter matching to the to the rutile phase. And as we keep on increasing the acid contents, we can completely synthesize the rutile phase, the 100% rutile TiO2, which is the rod shape. So this is what the schematic diagram, how the shape changes from anatase to have the shape changes from particles to rods, and then simultaneously change in their phase from anatase to rutile using a simple solution-based method. Then we studied the photocatalytic hydrogen generation performance with these different material synthesites, pure anatase, pure rutile. The name was like A1 for anatase, AR1 for anatase rutile mixed phase, AR2 again mixed phase, and R1 is a complete rutile phase. So it was found that one particular ratio of the anatase rutile gives the best or maximum hydrogen generation performance. And that is also this was also done by using a cutoff filter of 420 nanometer, a cutoff filter. using the visible light, and the results was also compared with P25. In the C diagram, as you see here, we have also done another experiments by mechanically mixing the rutile anatase phase with the same ratio, same quantity of the same percentage of the anatase rutile present in the AR2. And what we found that when we mechanically mix the anatase rutile phase, their performance was not as good as the synthesized material, because the actual heterostructure could not form, and the adhesion between two different phases or connectivity between two different phases in this material would not be as good as that when it is synthesized in situ, where both phases form simultaneously. So giving the importance of the heterostructure formation and their well connectivity between two different phases play important role in the charge separation. So in all these cases, we have also done several other studies, including like different amount of the catalyst was taken, different type of sacrificial agent was taken, and we have measured also in other conditions such as in the natural light. And here you see that how natural light also giving quite a good performance for the generation of the hydrogen. And we have also measured the in natural intensity of the natural light, which was around 90 milliwatt, as compared to the xenon lamp, which was used, artificial xenon lamp used inside the lab, which has 100 milliwatt per centimeter square, little higher. Natural sunlight intensity was a little lower, but still using a natural sunlight, the performance was found to be quite good. It is to be that is which is more important for practical application if we want to carry forward for large scale production of hydrogen. Photocatalytic mechanism is again estimated by or reduced using their bend position. So all those things I have not covered here, how the bend position was calculated, like conduction bend position, valence bend position, and how in this using the experiment by measuring the band gap, measuring the electrochemical studies, we can estimate their position, actual position of this conduction band and valence band position for pure rutile, pure anatase, and then again after finding their banded position, we found that their band position are lying with this energy scale, indicating that electrons can comes from electron can transfer from the rutile to anatase phase, and the holes can go from anatase to the rutile, making the charge separation possible in even the material is same. And the mechanism is here right side, where the how the electron holes are generated and the reaction is progressed to produce hydrogen. Electrochemical hydrogen generation again performed in the same set of sample, selected sample. In the first graph, the current density versus potential, which is a LSB curve, which was done in a light chopping mode. What you see is that means when light is allowed, the current shoots up, and while potential is increased versus reversible hydrogen electrode. So as we increase the bias potential, certainly the current density will increase, and current density increase means more hydrogen generation. At the same time, because we are doing the light on and off, that's why you can see the curve is going up and down, and they are quite linear in a manner that there is a stable way of producing electron holes, and they can therefore produce hydrogen in a linear scale without getting without sample getting corroded or sample getting disturbed due to long-term use. In the C, there is again charge transfer resistance measurements, impedance spectra, which gives lowest semicircle, small semicircle, indicating that smallest charge transfer resistance. It was again done compared with different in the D we have compared the hydrogen generation performance per centimeter square, because in the electrochemical work we caught it on ITO substrate, and therefore we measured here per centimeter square instead of measuring the per gram. In previous experiment, as you see, we are measured per gram, that is a mass density per amount of the sample. But in these cases, in electrochemical cases, we have measured per centimeter square, because here almost it was coated on a substrate, therefore per centimeter square. Then this is just simple schematic that, as you have seen, in the working electrodes or anode, the electron hole separation occurs, and then the TiO2 or this heterostructure is used, it facilitates water oxidation, producing oxygen here at the anode, and electrons will come in the outer circuits to the cathode, and hydrogen ion will come from anode to the cathode, at which hydrogen generation will occur. PL spectra was again confirmed to study that recombination effect. As we see that in case of this blue curve, recombination is less because luminescence intensity is less. We have done also the carrier lifetime measurement, etc. That I have not covered here. The reaction medium, what I have shown here, that reaction medium can be utilized to control the phase and morphology of the TiO2. And when you take, when we synthesize optimum percentage of penetrance in rutile, it can give better hydrogen generation performance. In addition to that, energy storage also we work, but let's comes to final summary. What I presented here, that we I give an example of 3 heterostructures: semiconductor, and metal semiconductor, and semiconductor with 2 different phases. And in all cases, when you form heterostructure, performance will increase. This is mostly due to the well separation of the charge carriers inside the sample, and thereby doing the oxidation reduction more efficiently. I would like to acknowledge the organizing team for inviting me. And also the work was carried out by mostly funding from the DST, CRB projects. And the results I have presented here all are done either by Momita Chandra or Dr. Kaushik Bunia, who has already passed out. These 2 students have contributed, the results of these 2 students I have presented here, so therefore I recognize them. So all the works was carried out by them. And thank you all thank you all for attention, and I would be happy to answer any queries or doubts.
Thank you, Devrata, for your nice talk. Now I invite the questions for Devrata. Audience, please kindly ask some questions.
Okay, if no questions, can I put a question, please? Devabrata?
Sure, Professor Samal.
Yes. So, see, we have been listening to this kind of lectures many times, with, of course, a little variation of materials. I find 2-3 problems. One is the light absorption between 400 to 900 visible range is substantially low. UV absorption is good, but not in visible, the materials. And the second problem, we find that when you go from solution phase to the solid phase, particularly in case of TiO2, agglomeration starts. And this high surface area, the surface area drastically gets reduced with time as you dry it up. And the third important problem that I several times ask many students is that we are doing this in pure water, but sea water or whatever contains a lot of other interfering metal ions. And these metal ions, they can also corrode the electrode. We have a lot of different kinds of species, anionic and cationic species in sea water. But all these results are in pure water. Okay, so could you please update like overview of my question?
Yes, whatever you have told, I agree with you. First point was light absorption. Light absorption certainly will be light. Actually, more light is available with the highest intensity in the visible light, not in the UV light. But the problem is that we do not have materials which can absorb that much of the light at the visible region. We do not have suitable material.
That is my question.
So for example, so therefore material development plays a crucial role here. Like most of the work also done in TiO2 or such kind of wide bandgap material, but comparatively less work on visible light. Though people try to put efforts on the visible light photocatalyst, utilizing some chalcogenides, etc., but their stability and other things remains a concern, unlike TiO2. So it has to be taken care, it has to be explored. how you can absorb more light certainly, and at the same time the material should be very stable to have produce enough number of electron hole pairs. So this is one concern. Certainly, I agree with you. And your another question was, we do research in control electrolytes. This is we do it for certain purpose, like it is quite easier. But if I talk practically, it would be very interesting to do in real seawater or water. But for that, more work is needed from the student side, particularly first doing the complete study of the what water they are using, what are the different ion present, and then after doing those things, they can come to do with a standard system, let's say TiO2, and see which ions are absorbing or doing the that means deteriorating the performance or improving the performance. In some cases, it may improve. I would not say it's always deteriorate. Like say iron oxide. Iron oxide also been utilized hematite, etc., for water splitting reaction. Industrially, people are also exploring those things. So in certain cases, it might improve or might not improve, but more work, thorough work is needed. First, you have to completely study the water, what you are using, and then step-by-step process in a standardization process, see how it is happening. And this is a good topic, like those who are working on these to explore and make a contribution.
And the third one was particle size reduction. I mean, surface area reduction with time.
Yes, and those things remain, like for example, what we have seen here. Those things I believe can be controlled, can be possible to control. It is not very difficult task, because we can use suitable type of like adsorbents, etc. Or like say, for example, in our cases, if we grow nanorods with a particular pitch distance, that is also possible, so that they cannot agglomerate like the nanoparticle starch. So it is not a very big task. And second thing, that in case one is using the surface, one is using a surface like electrochemical process, now one can modify the surface to a manner that it have more surface area, as per just simple area is concerned. Aerial surface area could be as high as possible. For powder aggregation, etc., is an issue. But again, those things one can do stirring. When the nanoparticle is there, one can use certain kind of like adsorbents, etc., to reduce to an extent.
Okay. I understand. Yes.
Thank you, Pradhan, and thank you to all. Thank you, organizer. Thank you, the members of the VSSUT for this organization. Thank you.
Begin. Please thank the chairperson. Begin. You are muted. Please thank the chairperson. Yes.
Thank you, Professor Ajay Kumar Patnaik, for kind consideration our invitations and provide us valuable time to OCS REMS 2020. And also I'll thanking you, sir, for smooth managing the technical section 4 on day 2. Thank you all eminent speakers for their valuable and scientific talk. Thank all participants for their presence amongst us. This reflects their commitment to the professions. With this, I hand over the section to Professor Sasidhar Samal, President OCS, to give the concluding remarks on day 2.
It is really a great pleasure thanking you people in this work who have been working very hard. Though it is a webinar, I know how much of effort that goes into making it all precisely successful. So we have come to an end of this meeting. I now may the participants may switch up, sign off. We have some discussion to make. Is